And welcome back, everyone. Hopefully this works better now. So, as I was saying before I messed up the audio, welcome to the hypervisor recap stream. And so in this stream, I'll be going over what I did over the past 13 streams, which were basically me writing a hypervisor. So I'm going to explain why I did that and how it all works. So give me a second just to get the chat in order. Looks good to me. Oh, that's kind of messy. Okay, cool. So hopefully the audio is good. So let's talk about hypervisors. So, well, what is a hypervisor? Hopefully you know what a hypervisor is, virtual machines and all that. But there's quite a few different types of hypervisors. So what I've been working on is a little bit special. Basically, this hypervisor is intended as a tool to help me discover how the hardware of the Apple M1 and future Apple Silicon chips works. So the idea is that to figure out how the hardware works, what I want to do is run macOS inside a virtual machine and pretend that, let it see that it's talking to the hardware directly when in fact it's not. And that way I can see what it's doing with the hardware and then use that to figure out how to control it. So let's look at a quick example here, and give me just 1 second to make sure that Twitter is aware of the new Less Broken stream. I think just take a second, but anyway, yeah. So what I have here is I have my Apple Silicon reverse engineering tool booted, and this is the screen from the Mac Mini. And this is just the console that you get when you start it up. And the way this works is that it runs on the Mac, and then from the PC via USB port, I can run scripts that access the hardware. And so what I have here is a shell that allows me to control the Mac in real time. So okay, there we go. So for example, okay, so we have here, so how does this work? Basically, the way you access hardware, the way you control hardware on almost any modern machine is by using a thing called memory mapped I/O. And the idea is that, if you have memory, like for example, if the machine has 8 gigs of RAM, so there's 8 gigs of space for me to write data and read data. And for example, I can do that. I can read some data from this address, which happens to be part of main memory. And there's nothing there. And I can write, 42 and read back. And it prints it in hex. But if I force it to print it in decimal, you see it's 42. So, this is just memory. And in this case, memory on this machine starts at this address and then goes all the way up to plus 8 gigs in this case. But if you want to control the hardware instead of read and write memory, the way it works is that the hardware just looks like memory. So you can read and write things that aren't memory, but rather are properties of the hardware. So, for example, at this address, this happens to be the register, which is basically memory inside hardware, that controls where the image drawn on the screen starts. So this is part of the display hardware. And if you can see here, the screen is showing this console, and it has this value, 423C, blah, blah, blah. So I can write that back, or nothing happens. But if I add, say, 1920 pixels times 4 bytes per pixel times 1 line, the whole screen goes down by 1 line, which you probably didn't see. So let's do 16 lines. You can see it's scrolling down. Let's do 32 lines. 128 lines, 256 lines. And you can see how the whole screen is now starting later because I'm telling it to read different parts of memory. And now there's some weird blue apples later, which is interesting. So there's for some reason, there's more data in the screen memory that we don't use. And if I keep scrolling, oh, look, there's another apple there, the Apple logo. And there's even more small apples after that. So that is kind of interesting. You can go back. So this memory location tells the screen hardware where to start reading pixels to put on the screen. And it's not just memory locations like that. For example, this address here, has to do with the format of the screen data. So if I write the same value back, nothing happens. If I write something else, the colors change because this is configuring it for a different kind of color format. Here's a funny one. If I put a 1 here, you end up with a weird overlay of the Apple logo, which means it's reading other parts of memory and blending them in some way or using it as a mask or something like that. So it's pretty interesting. Now, of course, sometimes you can work out MMIO like this. You can work out what these things do just by trial and error, like I'm doing here, right? I mean, you can keep messing with these numbers and like that. But see, that kind of broke the screen, right? It's blinking weirdly, and I can go back, change that, and that breaks the whole screen, and that doesn't seem to do anything. But now it's broken again, right? So you can try changing bits like that and see what happens, but it's not very intuitive. And for some things like the display hardware, where you can immediately see the result, then that's it. You can basically go through the entire thing and get a good idea for how it works. But for other hardware that is more complex or that basically has to be configured just right or it doesn't work at all, it's not really feasible to like brute force it, just trial and error, right? Just throw things at it until you learn how it works. Especially if it's hardware that isn't running when the OS is when you get booted, right? If you require a sequence of operations to make anything work, you're never going to figure that out just randomly. So then the idea, basically, what we can do is one of two things. We can either reverse engineer the software that Apple wrote, which would be like decompiler, disassembling the macOS source code. The macOS drivers. Some of it is open source, but very little. Most of the drivers are closed source. Only the core kernel is open source, so that doesn't help us with like all the interesting hardware. So, so we'd have to like decompile or disassemble the actual drivers, but that runs into legal issues, and honestly, it's not a lot of fun because usually the information that you need to figure out how hardware works is a small part of what the driver is doing. And there's going to be a lot of code, there's going to be a lot of complexity, there's going to be a lot of stuff that doesn't really get to the point, basically. You have to read through pages and pages of code to understand how it's doing one little thing. I've done that in the past, and it can be done, but it's not. I find that there are better ways of doing it, and one of them is that you can just poke at the hardware, and actually for some things like this display controller, this is actually much faster than trying to reverse engineer the code. But for other things, that's not feasible. So what I thought is, well, if instead of directly reading the code, why don't I just observe what the code does? So reading the code is called static reverse engineering or static analysis, and seeing the code run is called dynamic reverse engineering or dynamic analysis. And that can be using a debugger to see how it runs and stuff like that. But for drivers, since you're interested in how it sends commands to the hardware, what you can do is, well, just set up a system so that you can intercept those communications with the hardware. And that's actually how NVIDIA GPUs have been reverse engineered by the Nouveau project. The way Nouveau did it is that they wrote a Linux module that can basically intercept everything the NVIDIA driver does. And basically it sets up it sets up so that everything the NVIDIA driver does to the hardware ends up faulting into the kernel, and then the kernel can handle that fault, and their driver can log whatever the driver did and then actually do it. So that's one thing we could do for macOS. But I figured, well, these chips support virtualization. So why don't I, instead of writing a driver for macOS that tries to do this whole thing, just run macOS in a VM? And then I can basically pass through the hardware. So it's not a VM like, VMware or like KVM or VirtualBox or anything like that, where you're emulating a virtual, like you're not just you're running the code, you're running the OS on the CPU natively, but the hardware that it sees is all fake. It's all virtual, and like you can run KVM on a PC or on an iMac, and then the hardware that the virtual machine is going to see is some Intel for something X chipset or Q35 chipset that has nothing to do with the actual hardware on the iMac, for example. This is a little bit different. This would be a hypervisor that is very small and that mostly just lets macOS see all the real hardware. So also the real memory. There's no memory mapping. There's also one guest only. So there's no switching between multiple virtual machines. There's no sharing the CPU with other applications or anything like that. There's, basically it's just there to intercept what macOS is doing with the hardware and to provide a few convenient features. And that means that I can run macOS even when macOS doesn't really know or care that it's running under a virtual machine. And thankfully, Apple is interested in running macOS in under VMs, so it's not like they deliberately broke anything. And that was good for me because it basically all worked. Even though this is not something Apple intended, there's, as long as like the core macOS is intended at some point to be run in a virtual machine, which if you look at some versions of the kernel in recent Mac releases, obviously Apple is working on virtual macOS on Apple Silicon. Though they're doing it, of course, with the idea of virtual hardware, like a big, VMware type thing. But because they've been working on that, there's nothing sort of in macOS that is designed to just not work in a virtual machine, right? Like there's a few places where it might have been a problem, and they've already fixed those bugs. So macOS doesn't mind that we do this, that we run it in a virtual machine. The standard macOS, by the way, not any special VM version or anything like that. So that's great because it means that we don't need to do any weird hacks or patches to make this all work. It's implementing a correct hypervisor should work. I didn't know this when I went in, but because it did work, we know that it does work. So yeah, let's dive into it. Some people are asking, how do I know where these addresses are, where the different devices are? So there's a thing called a Devicetree, and you will see, I'm going to mention that later when I talk about how the hypervisor handles devices. But basically, there is a hopefully, I think I haven't opened that. Give me 1 second. Yeah, so hopefully, if I look at the display controller here, not here. I'll zoom in a second. Just give me a second and you get to the right place. Yeah, here. So let's take this away and zoom in the screen. So this is part of the description that tells macOS how the hardware is laid out. And there's a different file like this for every variant, every model of Mac. And in this case, you can see that it tells it that registers start at these addresses. And in this case, the 2 at the front is actually added because of the way, there's nesting. So there's a thing above display 0 that sort of remaps things. But basically, pretend there's a 2 here. So 3085, in this case, is part of this first range here, 3085. Actually, no, it's not. Hold on. Is this one? Now I'm confused. D085 is not part of that. Is it? Hold on. 3085. Now you got me, because I'm not sure which part of the which part of the device tree this addresses from, which is interesting. Oh no, I think I know why. Because actually the way you control the display hardware on these Macs is not directly like I'm doing here. It's actually, there's a CPU that handles all of that for us. So in fact, I'm not supposed to be doing these things with the display controller that I'm doing here. So yeah, this is not actually described in the device tree, but if it were directly accessed, it would be. So that's another thing, right? Not all the hardware is described by this device tree. So there's always going to be things that macOS doesn't need, or but which might be interesting. But yeah, so that's basically the idea. So let's look at how the hypervisor works. Just 1 second. Let's get this started. Okay, cool. Yeah. So what does it mean to run a hypervisor on ARM? Well, actually, let's pull up the documentation first. Vendor docs. A little bit. So if this is the big ARM v8 architecture reference manual, which explains like everything about the ARM v8 architecture. And obviously, this is 8,500 pages. Unfortunately, I don't have time to go through 8,500 pages on the stream, but we'll see what we can do. So the interesting things here are basically, if I can find it, there's an introduction, and there should be, execution state. So the ARM architecture can be in multiple modes, and these modes represent different privilege levels. Not the 32-bit ones, sorry. Yeah. So this is the part that talks about that. So there's 4 levels, EL0 to EL3. And by the way, this is another example of ARM documentation that is like not the easiest thing to understand. But basically, EL0 is user space, user mode. It's where applications run. EL1 is where kernels run, and EL2 is the hypervisor. EL3 is used for the security monitor or the trust zone, like trusted execution environment. And EL3 does not exist on Apple Silicon because EL3 is optional. So we only have EL0, EL1, and EL2. Yeah, here's the go. That's the thing about this doc, right? It starts confusing, and then finally there's actually a part that tells you how it works. So yeah, EL0 is applications, EL1 is the kernel, and EL2 is the hypervisor. So normally the OS, as in macOS, actually runs in EL2. This is part of a feature called virtualization host extensions. That basically means that the CPU is designed so that an OS that is normally going to run at EL1 can sort of transparently run at EL2 and still work as a normal OS, and then you can add virtual machine code to it, which is good for us because it means that macOS should be written to work in EL1 and then will be running in EL2 normally, because that's how it normally is the hypervisor when you run VMs. But the same code should also work in EL1. So in this case, what we do is we run in EL2 and we run macOS at EL1. And so the thing about the word hypervisor is that the word hypervisor is kind of very vague in that it doesn't really have a set of requirements, for something to qualify as a hypervisor. So in fact, I have this mini thing up right here, right? And I can quit this, and I can say tools chain load -- el1 build mini.macO, and what this is going to do, you can see right now that in the frame buffer here it says running in EL2. Oh, we don't have the EL1 thing anymore. Sorry, I used to have that. But I can cheat. I can implement that real quick, probably. Oh no, I used to have it in a different thing. Sorry, I have it in. Yeah, I got rid of this because of the hypervisor. But I have this chain load EL1 thing here, which probably can be made to work. Yeah. So you got a typo there. So let me just fix this real quick. Because I basically did I reworked a bunch of stuff here, so I need to fix that. But hopefully this will work. So if I do this, oh, it crashed. I think it's because I didn't chain load. Give me a second. If I, hold on, let me go back to that. Not EL1. It might be that I did something like this doesn't work anymore because of the XF and SPR stuff or something. But basically, it would have it would have worked. Not entirely sure what's working there, but basically what I'm trying to get at is that it is possible to just run the like anything you want at EL1. So you don't need to actually write a hypervisor to run something in EL1. It just means that then you can't really do anything useful. So yeah, if I don't break this, is it because of the stop copy or something? Probably. No, it should be there. Let's try that again. Oh, actually, yeah, because it's not region anymore. Sorry. Don't need that anymore. This is old code, so that's why it's a little bit broken. And hopefully this this works. So now it's running in EL2, and if I do the chain load EL1 thing, okay, that didn't work. Probably the SPR thing. Oh, it enables it in EL1, yeah. Is that just breaking on that? Oh, yeah, because of the region. Yeah, I do need the region thing for that. Basically, it would be like call equals p dot call. I think that should work. So this is the part where I am just kind of forgetting how this works. Actually, no, this should be fine with without doing it before the MMIO shutdown. So this should work if I just do it like this. This is what I get for forgetting that this didn't work anymore. Okay, let's see if it works now. Almost. Okay, it rebooted. Shutting down MMIO. Oh yeah, I guess I can't do the shutdown anymore if GXS is enabled. That's why, yeah. So I do need that. See, now this is not an explanatory stream anymore. This is a me bug fixing thing stream. Just 1 second. It'll take a minute. The proxy utils. Yeah, this thing exit up, call, and then call should just be call region. Yeah, okay, so that should be fine as pcall. hv.py. Yeah, this thing. Okay, so this should be. This should actually just work with pcall like that. I actually remember to not do that. Okay, so hopefully that didn't quite work. Maybe I should just give up on this. I think the address is wrong or something. This used to be a thing where like if callable union rx EL1. Oh, it should be 0. Yeah, I need. Okay, so I do need. Yeah, I do need that. So this should work like this. Okay, this is gonna work now. Maybe. Okay, load it normally, and then we're in EL2, and this was a waste of time for a dumb demo, but basically, yes. Okay, and now it says running in EL1. So this isn't a hypervisor, okay? This isn't really, it's literally not doing anything, right? But all of it's done is I ran this code again after switching to EL1. And we're in EL1. We're technically in a virtual machine now, but there's no hypervisor handling anything, right? So it's like a no-op virtual machine. But this does mean that the hypervisor can be implemented step by step. So you start with this, and then you start adding features and making the hypervisor useful. So in this case, how do you switch to EL1? Where for that particular feature, I have a thing here. And literally all you have to do is you call this EL1 call function, which is written in assembler. And basically, it has to make sure that EL1 is enabled, which there's a thing in a register for the CPU to make sure that EL1 exists, because you can be in like VM mode or not VM mode. And then basically it just like disables interrupts and make sure that it's going to set up the same configuration for enabling interrupts in EL1, and then it's basically set up to return. It's as if you were returning from an exception, as if you were returning from something that happened in EL1. And this is pretty common in CPUs, where the concept of returning from an exception is not really strictly about returning from an exception. It's more like switching the context of the CPU. So in this case, we switch the context to be an EL1, which is what this thing does. This number 5 here is configuring the execution state to EL1, and then that gets put into the register that tells the CPU what mode to jump to, and then the register that tells the CPU where to jump to gets set to this function here, and then there's another stack, and I reuse the EL0 stack for EL1, and then that jumps here, and then this just jumps to whatever address I want to go to. So you just tell the CPU to go to EL1, it goes to EL1, it runs at EL1, that's fine, but nothing interesting is happening. So to make the hypervisor do useful things, there is a register called the hypervisor control register. And if I can find it, here it is. It has a lot of bits. It has way too many bits. In fact, they ran out of bits and started to make an extended register because, but most of these we don't care about. So the interesting ones are actually at the end. So I'm going to go backwards a bit. So the first thing that you can do is enable what they call virtualization. That's a bad name. What it means is it enables VM as in virtual memory for the virtual machine. So that means that whenever EL1 accesses memory, instead of accessing memory directly, it runs through a translation table that we set up that tells it where each address in EL1 is actually going to be mapped to at the hardware. And this is how the entire MMIO tracing thing works. The idea is that I can enable this and then configure the CPU so that, for example, all memory, all RAM is mapped directly. So EL1 can access all memory that it needs, or at least its own memory, without anything interesting happening. But for whatever MMIO I want to trace, I will not map it. And so anytime that EL1 tries to access that memory or that MMIO, I will instead get an exception, and the CPU will say, "Well, you're not allowed to do this, so I'm going to go into the virtual machine, and the virtual machine is going to decide what to do." And so EL2 gets an exception, and then I can log whatever EL1 did and handle it. So this is the interesting part. Then the other interesting bit that we care about is these FMO and IMO, and basically what these bits say is when you get interrupts. When the hardware has an interrupt for the OS, instead of going and sending them directly to EL1, send them to EL2. So we can intercept interrupts, and both FIQs and IRQs. There's two kinds of interrupts in ARM64. We can choose which one of the two or both we can send to the hypervisor. There's also an SR thing, which we don't really care about. That's for system errors. And then when we have those intercepted, we can create virtual interrupts for the guest to see. So this is how we can forward things back to the guest. There's a bunch of other stuff we don't really care about. But the interesting ones after this is this one, TIDCP trap implementation defined functionality. This basically means that any fancy Apple-only things that the CPU supports at EL2 are not allowed at EL1. And anytime EL1 tries to use them, it will go straight to EL2 and we can handle them. But actually, we don't use this because Apple provided a way to be more specific about which features are allowed and which ones aren't. And that's not a standard feature. That's something Apple made up. So I use that instead. And then there's a few other interesting settings here, but those are the main ones that we care about. That's pretty much, yeah. So this is the VHE thing I talked about, but this is a whole different story. But basically, this is one part where Apple broke the ARM specification, and they forced this to be 1. You can't set it to 0, which is not allowed by the specs. So that's kind of sad. And yeah, that's most of it. A lot of these are not supported in these CPUs, by the way, because they're too new. Like nested virtualization is not a thing. So, okay, let's look at how the hypervisor works. So this thing, where I just jump into EL1 is sort of it's a dumb version. This isn't actually used in the hypervisor. Before I do that, let me show you what the hypervisor can do. So we can go straight to the demo, and then we can go see how it works. So I need to make sure that I'm actually running in EL2, and I make sure that I'm running the most recent version of Mini, because if I run an outdated one, it doesn't work. The host side here and the Mac side have to be synchronized. I'm going to put this screen on the left so we can see things a little bit better, and hopefully you can still read the text. And that's the screen on the right. And I'm going to create another window and detach it and put that here. And I'm going to open a terminal there, and I'll talk to you about that in a second. So we got the proxy client. Here we go. Got that. So the run guest. So this is how you run the hypervisor. And I'm going to take this off because that's just a test. So what this is going to do is it's going to, I don't need that anymore. It's going to run a guest. It's going to give me a shell before running the guest, so I can configure things if I want to. And then it's going to run this script before running the shell, which is going to configure the hypervisor to trace all the hardware, which is a lot. And then this is the OS that it's going to run. So this is a development version of macOS. So I have symbols, which means I can get back traces and stuff. And this is the kernel that I packaged, I guess. I didn't compile it, but you bundle it together into a kernel cache. And then these are the arguments. So the hypervisor is single CPU right now, so you have to tell it that it's a... Well, you don't have to tell it that it's a single CPU because the hypervisor will do that anyway. And then this enables the serial port and a few other things that honestly I probably don't need, but but it just helps. And the watchdog timer turned off is important, so it doesn't kill the hypervisor when I'm testing things. So if I run this, you'll see a lot of things happening. It takes a while because it has to load like over 100 megabytes of kernel over USB, and it's like compressing and then loading and stuff. So it gives me a shell after configuring. Basically, almost all the hardware is traced except for a few things that I am bypassing because they slow everything down way too much. And I can type start. This is entering the hypervisor shell. Type start to start the guest. And you're already seeing debug output here. So everything you see here is the guest reading or writing MMIO at different addresses. So this tells me where the CPU is executing. This tells me whether it's a read or a write and what size it is. This is the address that is being read or written. This is what that address is. And in this case, it's unknown. I actually know what this is. I know this is the Wi-Fi firmware that is loading now. I'm pretty sure. And so this is why it's a bunch of blob here. This is like all the firmware data. And you also saw the macOS start to boot with a special version logo. It does break the screen after a while and then comes back. I'm not sure why the screen breaks. I'll have to figure that out someday. But once macOS initializes the screen, it does come back. And this here is the serial log from macOS. But the interesting thing is that this is not a serial port. So this is actually going over USB. The hypervisor virtualizes the serial port. It's one of the very few things it virtualizes. And it runs a virtual serial port that then gets redirected to USB. So there's two different USB interfaces on the same cable, basically. And that way you can get the serial debug without a special serial cable, which is not standard. So all you need to do to use this is plug in a single cable from a Type-C port on the Mac Mini or whatever other Mac it is to any computer. It can be a Mac PC or whatever over USB. And it shows up as two USB serial ports, one for controlling things and one for the virtual. Yeah, and we're back. And one for the virtual serial port for the OS to use. And the cool thing is that, for example, I can break into it. I can say Control-C. It takes a second because like there's so much stuff going on that there's buffers. But once the buffer's clear, you can see there's a shell. And I can even get a backtrace of where in the kernel we are. In this case, of course, it was accessing the audio-video decoder hardware, so it makes sense that we're in the middle of the Apple audio-video decoder driver. And you can see how it all started from some, like, I have symbols for the core kernel, but not for the driver. So for the driver, I just know which driver I'm in, but not the actual function names. And I could change what I'm tracing, for example. I could reconfigure it to not trace some hardware, and then you can just type continue, and it keeps going. Or I could break, and I could even inspect registers. I can, like, ctx.reg0, and that would be the ctx, sorry, hv. That would be the, don't even need to print it, actually, just show it like that. That would be, register 0, register 1, 2, 3. Or I can, this is the address where we have to return. I can show the stack pointer, which in this case there's two of them because there's a user space one and a kernel space one. So like that would be the user space one, that would be the kernel space one. And just continue. So it's basically kind of a debugger. It's a very basic debugger, but it's basically a debugger. And you can see it's actually booting now. The broken screen is my capture card, by the way, don't worry about that. But that's macOS running and showing all the hardware accesses in real time. And it's not even that bad. I can log in. It is obviously a bit slower than usual, but the fact that like it's not running at like 1 FPS or something is honestly pretty good, considering that I'm literally logging every single individual hardware access one by one. So yeah. And yeah, someone asked, I think, about how it knows what hardware is. Yeah, so I mentioned there's a Devicetree earlier, so I'll show you later, but basically the hypervisor knows, goes to the Devicetree and looks at what addresses everything uses and then makes a lookup table so that whenever all of these logs come in from the hypervisor, it can show, nice readable names and and tell me what all the hardware offsets are. But yeah, like this runs, and it's not even that bad. The network takes a while to come up, so that's why Safari here is going to take a while to boot, and also it keeps trying to initialize Wi-Fi. I don't know why that's so slow. Like even if I turn it off. But like the GUI isn't that bad. I can like pull up a terminal, and it doesn't take that long to start. A little bit, but like that works. And again, this is tracing the hardware in real time. It's still, a bunch of logs. Like that's the other thing. It's still booting, right? It's doing a bunch of random crap in the background and stuff because macOS does that. So it hasn't technically finished booting yet. So yeah, let's leave it running for now while I show you how this all works. So how do you make a hyper? Oh, there you go. You got the website. So how do you make a hypervisor? I think I should have gotten some water. I'll go get some later. But basically, so it all starts here in hv.c. And actually, by the way, the hypervisor, the whole thing is not that much code. There's like 100 lines of code here, another 100-ish here. The virtual serial port is like 40 lines. The whole virtual memory thing is the biggest part of the hypervisor, and that's like 800 lines. Exception handling is about 300 lines. There's not much assembly, 173 lines. I didn't write this. This was contributed later for the interrupt tracing, and then the Python side is also about 900 lines. So in all, that's what, like probably 2,000-ish lines of code or so, something like that, which isn't that much for a hypervisor when you think about it. So yeah, let's go over it. So the first thing you do is initialize the hypervisor. And that's done here. And so first it shuts down PCIe because macOS hates it if PCIe is initialized. And then it starts the secondary cores because I do use one secondary core for something, which you can look at later. There's a watchdog. And then it enables the physical timer for EL1 so that the guest can access the physical timer. There's actually 4 timers in ARM. A virtual timer, physical timer, and then a hypervisor virtual timer and a hypervisor physical timer. So as far as I'm concerned, EL1 can access both the physical and the virtual, quote, virtual timer, not the hypervisor ones. So this just enables that. And then it initializes the virtual memory, the page tables. So we'll look at that later. Then it configures that register that I mentioned earlier, the HCR EL2 thing, and these are the default settings, which basically enable things that should be enabled for the guest to work. It traps, which means it goes to the it takes over any errors from the hardware. This is forced, and then it has to be a 64-bit guest because these CPUs don't even support 32 bits. If we have any hardware errors, that gets trapped too, and then it enables the virtual memory. The guest doesn't have any exception vectors originally, so that just configures that to 0 by default. And then it figures out how often the hypervisor timer is going to fire. So the hypervisor has a timer, and I'll get to that later as to how that works. And then it cleans up. This is kind of partially cargo culty, but basically it's a memory ordering thing. So that after all of this is configured, like the caches inside the CPU don't have stale data in them and stuff like that. So this just initializes the hypervisor hardware. Right? And then when we want to start the guest, what it does is it reconfigures the exception vectors of many of this framework so that they are the hypervisor exception vectors. Basically, the normal operation when I'm using this Python thing is designed so that I can run experiments at EL1 and it will do some magic to like forward them to EL2, and it's meant for development. But once you run a guest at EL1, I need to handle everything that EL1 does in terms of a VM guest. So the way that I will handle all of that changes. So this switches over the CPU to use these exception vectors, which is the next thing we're going to look at. Then this is also, I'm also going to mention this a little bit later, but this is a special Apple feature. Then it starts the watchdog timer, which I'll also get to that, and it sets up the hypervisor to wake up, to break the guest a certain number of times per second. And then finally, it enters the guest. So that is part of this assembly code where this is the equivalent of what I had earlier here for what I mentioned for the call EL1 thing. So if you look at this code, it's going to be pretty similar. But basically what it does is it saves a bunch of registers, and then this is the same code as here, as you can see. It switches to EL1, it initializes a few things, and then goes into the guest. So this is just the switch to EL1 part. But remember, once we're here, we've already enabled virtual memory, and we've enabled more hypervisor features. So that's why this is a little bit different from the dumb just run in EL1 mode thing. Because now, whenever the guest does certain things, it's not going to be allowed, and we're going to get a trap. And so that is where the exception handlers come in. So that exception handler table that I mentioned before is this one, hv vector start. And honestly, I should comment this. So why don't we do that right now, actually? But basically, if you go to the ARM manual, you'll see that there is, and I keep forgetting where they put this, the exception vectors in here. Yes, exception levels, exception entry, exception types. I will find this. Yes, there we go, exception vectors. So there are actually 16 exception vectors on ARM. And they are at these relative addresses, right? So these first ones here are current exception level. So basically EL2 with SPEL EL0, which are not used. These four next ones are EL2 with SPEL2. These four are for 64-bit mode for guest in 64-bit mode, and then these four are 32-bit, which is not used in the CPUs. So the CPU basically splits which function it calls to handle different exceptions depending on where they came from. So this should never happen, the EL0 ones, because we never used this mode, basically. These are the exception vectors for when the hypervisor has an issue, for the hypervisor has an exception. So these are the standard handlers for example, if I'm in the shell here and I can break it and I can do a read from an invalid address, and this tells me that the hardware failed to do the read from that address, and this information comes straight from Mini, and this is all it has nothing to do with the hypervisor. This is just my standard sort of recover from errors code for experimentation, right? So in this case, I get a bad idea, which is like my marker for there was an exception, and we couldn't actually read the data, and so that's what these take care of. So that is used whether we're in the hypervisor or not. And then these are the ones that are used when the guest is running. It runs vector, hypervisor, sync, IRQ, FIQ, system error. So there's 4 different types. Sync is used for most normal exceptions. It basically means the guest did something that it's not allowed to do or that we chose to trap. IRQ and FIQ means the hardware needs attention. So you got an IRQ or an FIQ request from the hardware. And S error means system error, which is actually the hardware saying that there was like a deeper problem with something. Mr. Spark asks, does the OS have any chance to know that it's running on hypervisor? Yes. The OS at all times can know that it's running in EL1. ARM does not support transparent virtualization. There's really no easy way to make a VM on ARM that looks like it's not a VM. With nested virtualization, you can at least have a VM that is, that can still use VM instructions and sort of pretend EL2. but there's holes in that in sort of that facade. Like it's not intended to be completely invisible. And these CPUs don't support nested virtualization, so there's no reasonable way to sort of hide a hypervisor from the OS. And I actually consider that a security feature. Because it means that you can have like malware that hides itself as a hypervisor in a way that the OS can't tell. All of this works because macOS doesn't care that it's running inside a hypervisor. There's very few places in the OS where it would care. And those places are already set up to work because, again, Apple is obviously working on making this all possible anyway, under different circumstances. So there's nothing on macOS that needed patching or that broke or something like that, once I understood how I had to set up all the hardware. So yeah, basically, once you jump into EL1, that's the guest is running, and if anything happens, it's going to end up at one of these 4 places. And all of these do the same thing. They just save registers from the guest. And then here's an interesting one. I'll go there in a second. But it saves registers, and then it jumps to the C code that actually handles these exceptions. So here's one that actually, this is one of the things that I had to spend a bunch of time on, which is ARM has a feature called privileged access never. And the idea is that it's meant for OSs to mitigate exploits where the OS is accessing data in user space, even though when it's not intended to do so. So it basically stops the OS from accessing application data in user space, except when it chooses to do so. And the thing is, in Mini, in this code base of mine, there is no such security because actually everything is accessible by user space because I want to be able to run things in EL0 for experiments. So, there's all memory is accessible by user space because user space is just my own code anyway, right? So, in fact, if you enable privileged access never, Mini can't access any memory whatsoever, not even the stack, and everything breaks in a horrible way because you don't even get, any error messages because literally nothing works. So, unfortunately, ARM has a design quirk where even when you're running a VM, if the guest enables privileged access never, that leaks into the hypervisor. So what I had was that when I was running, everything was working fine until the guest enabled pan, and then I had a hypervisor exception, and then the hypervisor was dead. And that was quite annoying to debug. So the first thing I need to do whenever I get back to the guest is make sure to turn this off. And I don't have to turn it back on because actually returning to the guest will restore this from the saved state. So I don't actually know why ARM didn't have a bit that... There's actually a bit that forces this to on in this situation, but there's no bit to force it to off. So I just have to do this. But yeah, I don't know. So yeah, once the guest does anything interesting, it does a little boilerplate, saves state, and then goes into the C code. So let's look at the C code. And it kind of starts at the bottom here. So this is the general flow of everything that how the hypervisor handles anything from the guest, any exception from the guest. The system error 1 in this case actually doesn't go through the guest because we're not expecting it. But basically, these breadcrumb functions are basically logging about what the hypervisor is doing. Then it runs a common function on every exception entry. Then it handles the exception, or in this case, it doesn't. And then it exits. It does a bunch of code that runs on the exit of every exception, and it logs that we're out. So the system error 1 is the simplest one because we never expect to get a system error. So what it does is it immediately jumps into Python. The way this Mini thing is architected is that if we go back out of the hypervisor for a second and go back to the main, literally the main function of Mini, after initializing, it runs into run actions, and then that will run the UART proxy. And that is the loop that waits for commands from the PC over USB and just executes them. So that's the thing with it implements the protocol to receive messages, and you can read, write memory, or run proxy calls. And then there's like this whole giant list of functions that you can call from Python, and it all goes through USB. And it's basically a remote procedure call implementation. Effectively, it's just a bunch of different functions and requests you can send to it. And one of those is the hypervisor stuff, right? Like hypervisor init calls that hv.init function, hypervisor map start. We'll look at some of those later. So to give you an idea of sort of the execution flow here, when the hypervisor is being initialized and started, that's happening from the Python side. The Python side is going to, this loop is going to be running in the context of the main function. That's going to be waiting for commands. And one of the commands you can run is hypervisor start after everything is initialized. And that's going to jump into the guest. So we're still inside this loop, but now we're running the guest. And then, unlike if you've seen how other hypervisors work, like Apple hypervisor.framework or KVM, you might be familiar with the concept of like executing guest code, like entering the guest, and then whenever the guest does something that we need to handle, that function returns, and it's a guest exit code, and it tells you why you need to handle something, and then you handle it, and then you call that function. You keep calling the function to keep running the guest. That's not how this hypervisor works. In this hypervisor, this function, hv.start, never returns until the entire guest is shut down. So this can return if we quit, but other than that, it never returns. So what actually happens instead is that once we have a hypervisor exception that requires attention from Python, it runs this hv.exception proxy function, which is up here. And what that does is it collects information about what the guest is doing right now into this structure. And then it, including the registers, and then it builds a message to send to the host, to the Python, saying, hey, I'm going to run a new proxy. I'm going to start accepting commands from Python. And the reason for that, which normally is one called boot, which is the one you get when you just start Mini. In this case, the reason is whatever came in here through reason T and the code, which in this case would be there's an exception from a lower level, so from the guest, and the exception is an S-error exception. So for that reason, I'm going to start accepting commands from Python until Python tells me that we're good. And so it suspends the watchdog timer, and then it runs the proxy again. So this is re-entering the proxy. All the proxy code is using stack buffers and stuff like that, so it's safe to run from itself, basically. And so that's what this is doing. So you can think of it as a nesting thing. The Python starts the hypervisor, which then starts the Python handlers again. And that's how we can handle exceptions from Python. So, and then once that returns, Python, the way that works is that there's one command from the proxy that is basically quit, exit. And that returns a return value, and that tells the hypervisor how to proceed. So if it's handled, then we restore all the information about what the guest is doing, and we return. Another option is that we want to exit the guest, and then that actually runs some code that basically kind of does a stack switch. Like this exit guest is basically unwinding the stack instead of, like, this never returns. This makes the enter guest function return. So if you've ever done set jump and long jump in C, it's kind of like that. So this is not normal control flow. This is a hack. But other than this one, basically what we have is a clean nesting of control flow. So the proxy starts the hypervisor. That doesn't return, but the hypervisor can decide that it needs the proxy to handle something else, the Python side. So it calls back to the Python side. The Python side does something, tells the hypervisor that it's fine, that you can return to the guest, and then it keeps happening until the Python side decides that, okay, we want to shut down the guest, and then that goes back all the way to the original start guest call, and then finally we're back at the main function that is handling Python requests. Which, by the way, doesn't mean you can run the guest again, because like I don't have a function to clean up the hardware so that you could actually run macOS. So you still have to reboot every time you run macOS. But at least you can technically exit, and you could exit and then, for example, inspect the hardware to see what macOS did while having shut down macOS. But it doesn't really make a difference because you could do it without shutting down macOS anyway. So that's the case of when something is not handled, like the system error, which is only handled by Python. However, same with interrupts, because interrupts are actually sent directly to the guest, so we don't expect this to ever fire. So if it does, then Python handles it. But the interesting one, the most interesting one, is this sync function. So someone is asking if you could do this without Python. Yes. So here's an example of how it works without Python. In this case, when we get a synchronous exception from the guest, it means the guest did something that we need to handle. The beginning is the same, but then we get this register, which is the exception syndrome register, and that tells us what happened. So in this case, this handles 3 different types of exceptions. Abort lower means that the guest accessed memory that we forbid it to access. And in that case, it uses this function called hv abort. MSR means the guest accessed the system register that we don't allow it to access. So in that case, we call this function handled MSR. And this is the custom Apple thing exception. In this case, when we decide to trap only certain custom Apple features, instead of ending up with this standard exception, it ends up in a non-standard exception. And then that's a subcode that tells us that it was a system register access that is one of these custom Apple ones. And we use the same function to handle both of those. But then which system register is encoded in a different register. So that's why this is different. So this way I can use the same function to handle, Apple exceptions and standard exceptions. And, the information is in a different place, but I pass it as an argument, and I can handle the same thing. And then all of these functions have the ability to say whether they handled the exception or not. If they did, then I skip the instruction, because these functions are supposed to emulate whatever the guest was trying to do, that one instruction. So if they were handled it correctly, then I add 4 to the instruction pointer, to the link register, which is where we're going to return to the guest, which means it's going to skip the instruction that caused this fault. And then we just exit. So whenever the guest does something that we can handle, we do it ourselves, possibly in a different way from how it would normally been done. And then we skip that instruction and keep going. If it's not handled, then it goes back into Python. So this is how I can, you could do the entire hypervisor this way in C, of course. And in fact, most of the time, that's how it works. Most of the time, it never goes to Python unless something is explicitly, unless we choose to do that. And that's how I can make it reasonably fast. So we only have to break to Python when something interesting happens that the C code doesn't handle. So let's look at the MSR function first, because it's a little bit easier than the data abort function. So when the guest access is a system register, which means that it executed one of these 2 instructions, some register, or MRS, or MSR, basically either reading or writing a system register, we get the information about which register it's trying to access in this in this argument, which, as I said, is different depending on whether it's Apple or standard. And this is the encoding, where it has like OP0, OP2, OP1, CRM, CRM. And then it also tells me what register it is using. So what general purpose register it's either reading the system register to or writing from, and whether it's a read or a write. And I'm not going to go into how these there is a macro here, and there's a stream for that. But basically, I have a lot of fun preprocessor stuff to make the standard names that I use for system registers also work as an encoding for that I can switch on for handling them. So you can dig into the header files if you're interested in that. There's some weird. There's a whole stream where I spent like an hour on this or something. But basically, I have a couple convenience macros here. Pass means that if it's this register, if it's a read, it just reads that register and writes the result to the general purpose register that the guest is trying to use. Otherwise, it writes the register from the general purpose register that the guest is trying to use, and then it returns true, saying we handled this properly. Sysreg map is the same thing. The difference is that instead of reading from the same register, it reads or writes from a different register. And this is important when because of the way VHE works, some registers are split between the EL2 version and the EL1 version. But to enable an unmodified OS to run at EL2, what happens is that the EL1 version of the register is redirected to the EL2 version when you're running an EL2. So if we were to read the same register the guest is reading, we'd be reading our own version of the register, not the guest's. So there's a different register name that lets the hypervisor actually read or write the guest's view of that register. Those are the ones that end in EL1-2. So you can see that this register, which I don't even have a name for, it's some kind of timer. I don't know what it is, but I know that it gets used very often. So I want to put it in C so Python doesn't have to handle it. But this one, for example, is a standard register called ACTLR EL1, which Apple decided to add a separate bank for EL2. So they implemented this. The standard ARM, like ACTLR EL1, is a standard non-standard register. It's a standard register that is implementation defined. So like Apple says this exists and it has a name that doesn't say that it's implementation defined, but it's not like, it's already been defined by the spec, but the actual meaning is all custom, which is kind of funny when you think about it. But there's an EL1, EL2, and EL3 one. And because Apple decided to use this, but the official ARM spec didn't define this redirect feature where the EL1 one actually goes to EL2, Apple said, oh, well, we'll just add that ourselves. And so they added this EL1-2 version, which is how normally, it's not in this list, but there's a different here in the ARM virtual memory architecture, host exceptions, aliasing. So there's these EL1-2 versions of all the registers, and that's how the host can access the real. So when the host accesses this, it'll get EL2 instead. So if you really want to access the guest version, you need to use this EL1-2 thing. So Apple did the same thing for this register because ARM didn't. So this custom Apple EL1-2 is how you actually access the guest's ACTLR EL1. So that's why I need this sysreg map thing. So there's more passes, some performance monitor unit stuff. Inter-processor interrupts are also passed, but then there's special handling for the interrupts. Basically, I virtualize whether an interrupt is pending. So when this is used when the guest wants to send an interrupt from one CPU to another, but it also happens from one CPU to itself, which is why I need to make it work even with one CPU. And basically what happens is that when I get the interrupt, I clear it so that we can continue running, but I make a note, and when the guest asks if it's pending, I use my own flag. So this register is virtualized. And this is another performance counter register, which is virtualized for the same reason, so that the interrupts work. So that's how this works, right? You can have ones that are passed through directly, ones that are mapped to a different register, and then others that are actually implemented in code and virtualized in some form. Yeah, Mr. Spark asks if this could be a remote GDB session. Yes, so that's an idea for the future. Basically, I need to make this work as a proper debugger with GDB. I'm missing features for breakpoints and single stepping. So if I add support for the debug hardware on these chips, then I could have those. And then the Python side could implement a GDB remote stub functionality that translates to my custom protocol here. And then you could use real GDB with the hypervisor. Yeah. So that's not implemented right now. But you saw that there is some debugging features, right? So definitely it can be done. But the main thing that's missing now is like breakpoints and single stepping. So that's how you handle system registers. And by the way, in case I think I haven't mentioned this, system registers are not MMIO. They are registers that are accessed directly with special CPU instructions. So they're kind of part of the CPU. So I'm going to get a bit of water, and then we're going to get to the next big thing, which is virtual memory. Okay. And we're back. So, yeah, that was system registers. Let's look at virtual memory. That is this function here, hv.handle_abort. And before we get to that, I have to explain how the virtual memory works. This is the largest file in the hypervisor. Thankfully, you don't need to care about most of this in detail, like line by line, but I can give you an overview of how it works. Let me answer a few questions first. So some 8090MO asks, if virtualizing the single core for the guest, does that mean supporting a second guest would be possible within reason? If you mean running different guests in different cores, yes, but they couldn't share the hardware. So if you gave them access to the same hardware, they would get very confused. But it is possible to run like, yeah, different pieces of code on different cores. I do intend to support multi-core in the hypervisor eventually. It's not terribly hard. Basically, I have to virtualize the hardware that lets macOS start the other cores so that I configure them properly. And then I need to have some locking, obviously. I think most of the hypervisor code doesn't need locking. There's a few things that need to be changed to use per CPU data. And then, most importantly, the Python thing needs a big lock. So anytime any of the cores has to have Python's attention, there's going to be a big lock around that. And obviously only one core can be, having an exception handled by Python at any time. It might also be useful to, whenever Python gets invoked, like use some of the CPU debug features to halt the other cores so that, the guest doesn't run crazy in the other cores while Python is handling something. Because that could cause timeouts and things, so we probably want to stop the world whenever Python gets called. But yes, it should be possible to support multi-core in the hypervisor. So, and then Piero Uloa asks, as far as I see, Mini has a freestanding C part for the target and a repo for the host. Yes, that is correct. So I'll look at the Python later. But there's not just the REPL on the host. There's a bunch of hypervisor implemented in the host. Basically, the rare paths, the things that are not time sensitive, are implemented in the Python, and also things that can be made time sensitive, which are, there's some hacks in there for debugging, basically. So, but actually, I think the C side is easier to understand. So I wanted to cover that because then the Python side is going to make more sense. Otherwise, it's going to be like, because a lot of the Python is similar to the C. So this is how the virtual memory is handled, and this is the this is definitely the most complicated part of the hypervisor. So I should go over page tables. The way OSs handle memory and the way hypervisors handle memory is actually the same way, which is that the CPU has a bunch of tables in memory that tell it where to map one virtual address to one physical address. In the case of an OS, a virtual address is an address used by user space or by the kernel itself. And that's how different applications can use different parts of memory and not collide. And in the case of a VM, what happens is there are two levels of page tables. One is the guest's OS page tables, and the other is the VM's page tables that then apply a second translation. So this is why that's called stage 1 and stage 2 translation. And someone's asking, how does the CPU, the Python code interoperate with C? Don't worry, we'll get to the Python code in a minute. So the CPU is going to do this whole process twice. Once to handle the operating system part running inside the guest, and then, what the guest thinks is a physical memory address isn't really. It's actually called an intermediate physical address, an IPA. And then that's going to go back through the hypervisor page tables and get translated to a real physical address. Or if we don't map it, then it faults. And that's how I can trap or intercept accesses to the hardware. So there's actually a nice comment here that explains how this all works in the context of the hypervisor. The way page tables work is that if you actually were to have a giant table mapping every single address to every single address, you would use a ridiculous amount of memory. So instead, it's actually a tree of tables. And each table points to more tables so that you only use the parts of the tree that you need, and everything else doesn't exist in memory, doesn't take up any memory. In the case of this hypervisor, and there's several ways of configuring it, but in this case, there is a 64-bit physical address size for the guest, so only 36 bits of address are valid for the guest. And this is actually a limitation of the M1. It confused Linux a little bit. There was a patch for that, but it's enough for 16 gigs of RAM, so it's fine. I assume they'll increase that in newer CPUs that need to support more RAM. But anyway, to support translating 36-bit guest addresses, we need 2 levels of page tables, or 1 level if we use large mappings. So the 36 bits are broken down into 11 bits, and 14 bits. These 11 bits will choose the index into the first table, the root table. Then that will either point straight to memory or point to an L3 table, which will then take another 11 bits of the address and find where that chunk of memory is supposed to map. And then that finally, pages are 16 kilobytes, by the way, which is why this is 14 bits. So this will point to a 16 kilobyte block in memory that is directly mapped to the guest. If there is no L3 table, we can take a shortcut, and this can point straight to a 32 megabyte chunk of memory, and that way we save a bunch of time and space if there's big chunks of memory that need to be mapped. But there is another cheat that I add. The hardware only supports 16K pages, so we can only choose to map memory in 16K chunks. But for MMIO tracing, I want to have a finer granularity than that. I want to be able to say, I want to trace this one 32-bit register only, and then, like nothing else. Now, I can't have the hardware do that. The CPU is going to have to fault on the entire 16K page, no matter what. I can't have it only fault on a chunk of the page. But what I can do is then in the C code, implement a virtual level 4 page table. So the CPU doesn't know about this, but I can use the same structure basically to have an extra level of page table. And in this case, I actually use 12 bits instead of 11 bits. And then that tells my code where to map every individual 32-bit word of that page, which is actually 64 bits in the page table. So at this point, the page table is twice as large as the memory you're handling. But because this is used rarely, that's okay. And so I can have a mask for every single 32-bit word of that entire 16K page, which can tell my code what to do. And it could be trace it for tracing reads, tracing writes. You can hook it. You can do a lot of different things. So this allows me to have that very fine control, which is important for performance, because it means that I can only send to the Python side exactly what I need to from the tracing with surgical precision. So this is basically extending this page table structure that the CPU supports with one extra level that is all software-based. Hardware doesn't know about it. And so the way these hardware page table entries work is, I would look it up in the manual, but I can never find the damn thing here. Let's see if I can find it in less than like 20 seconds. Virtual memory system architecture, memory access control, memory attributes. No, where's the page table entries? I can never, yeah, table format descriptors. Is it these? These maybe? Yeah, somewhere here. Yeah, okay, I found it. Basically, this is the structure of that entry in the page tables. And depending on the configuration, there's a whole bunch of different ones, and you can see that it's pretty it's kind of confusing. But and like level 3 is different from level 2 for some reason, and yeah. But basically, if the low bit is 0, it's invalid. If the low bit is 1, then the next bit tells you what kind of entry it is, and then it points to the next entry or the memory address, depending on what level it is. So this is level 3, 1, 2, I forget what those are. It's level 3, level 1, 2 should be somewhere else. Yeah, I forget what that is. But anyway, yeah. So that's the hardware format. My software format, basically what ends up happening is that if the page table entry is not valid, then that's something for me to handle in software. And I reuse the same page table structure to tell my hypervisor what to do with a given address, as well as to tell the CPU what to do with it if I want the CPU to handle it directly. So these are the standard attributes that we use for hardware page tables for the CPU to handle directly. But in the case of software entries, in the case of something that the hypervisor is going to look at directly, I have my own definitions. The software page table entry bits, which in this case have a bit for tracing reads, a bit for tracing writes, a bit for requesting synchronous tracing, which means it's slower but safer, and then a type, which means it can either map to another memory address, it can either run a C function that is a hook for virtualizing hardware, or it can run a Python function, which is a hook. And in that case, it can choose whether it only hooks on reads, on writes, or on reads and writes. And then I have a bunch of macros to figure out what kind of entries they are, because trust me, this gets very confusing. So I'm not going to go through this line by line because it's going to be a giant mess. But basically, hopefully this is enough to give you an idea how it works. So there's an initialization, which configures all this hardware for mapping things in the CPU with the right settings. And then it tells the CPU that the page tables start. The root page table is this level 2 page table, which there's just one, which is just a static page table here. And then there is a lot of functions. And this is a lot of code to handle individual levels of the page tables. It can delete page tables. It can map new things from the page tables. It can get a new page table and allocate one if it needs one. And because all the levels are a little bit different, hold on. Someone, Rowan James is talking about the embedding section of the Python docs. Rowan, you're actually kind of confused. This is not Python embedded running on the Mac. Python is running on the host and it's connecting via USB to the Mac. So there's no embedding of the Python. It's a standard Python interpreter running pure Python code. There's no C Python interrupt at all. What I have is Python running on a host, communicating over USB with C code running on a target. So there is no like C code involved with Python directly. They're running on different machines. So okay, so back to this. So yeah, I can't go through this line by line, but basically the idea is that if I want to get a new page table, I'm gonna look it up in the previous page table, and then if I find it, I can just return it, and if there is none, then I can allocate a new page table and set it and clear it up. And so this is all designed so that if you say have a 32 megabyte block of memory, that's why this is complicated. If you have a 32 megabyte block of memory already mapped, and then you try to map a 16K page inside that, it actually goes and splits it into a 16K mapping with the equivalent mappings from the 32 megabyte block. and then changes only the one subpage that you're trying to map. So this is how I optimize sort of a page tables, right? You can have a big mapping and then it'll break it down into smaller mappings as you try to do more complicated things. And that's why there's all this code, which is fairly repetitive and confusing. But the main entry point is this one, which is hv.map, which says take this address, this intermediate physical address, map it to this physical address or special thing. This is how much memory we're going to map. And this is how much I'm going to increment the to address. So in practice, this is going to be either 1 or 0. That means that either it's mapping, quote, from one address to the one sole place, or it's actually mapping to contiguous memory. And you might think it doesn't make any sense to map, a whole range of memory to one place. Well, that's used when I'm not mapping to physical memory, but rather when I'm using one of these hook modes. So the code is the same regardless of whether I'm mapping to physical memory or I'm setting up a hook, but this too includes the attributes and includes the bits that tell it whether it's valid or not. So I can, if it's not valid, this represents a software page table entry, and then this encodes, like this could include the C function that is a hook or something like that, right? So this is how I reuse the same code regardless of what I'm doing. So increment is what allows it to correctly add to the to only when it's a real address and not add when it's just, a C function or something. So this is doing, sort of this small to large thing where it maps as many small pages as it needs, and then eventually, if it's aligned, it can use a bunch of big mappings and then going back to small. So this is all just optimizing. But in the end, what this implements is these functions, right? I can unmap things, which means mapping to 0, which means it's not valid. And 0 in the software sense is a special value that means not mapped, abort to Python. It can do a hardware map, which means it's a direct map from to, and in this case, it has to specify the attributes for physical page tables and that it's valid. And of course, in this case, the increment is 1 because we're mapping to physical addresses. So, 1 goes to 1, 2 goes to 2, 3 goes to 3. Map software is the same thing, but in this case, it uses emulation. So it doesn't directly map through the CPU, but it still requests that memory be mapped to contiguous physical memory. And in that case, it tells it that it's a software page table of type map. So the increment is still 1 in this case because it's the to address still represents a physical address. There's one interesting quirk here, which I don't think I'm ever going to use, but it might be worth mentioning, that when you use the hardware maps, it can only map from a 16K aligned address to a 16K aligned address. And it can only map, you can only use 32 megabyte aligned mappings if the destination is also 32 megabyte aligned. That limitation does not exist for software maps. So I could map to a weird unaligned address and it would work. I can use a 32 megabyte map, and the destination, the from has to be aligned because the hardware has to represent it as a 32 megabyte unmapped address. But the two can be not aligned and it still works. So that's kind of a curiosity that the software mode supports weird, crooked mappings like that. And then hook means that it's going to call this C function. So in that case, it sets the type to hook, and then the to address is actually just the C function pointer. And then the emulation code is going to look at that. And then proxy hook is what I mentioned, where in this case, the ID is encoded in the page table entry, and that's just an ID for the Python side to then map it to a Python function. So the Python side keeps track of what each ID means. And then it uses the hook type. And actually, this is wrong because this is useless because I just realized that you can't actually set the... this is wrong. This should be Python hook. So I never use this function because actually from the Python side, I just call hv.map directly anyway. So I should just delete this because this is not useful from C anyway. That's never going to be called from C. I'll commit this later, but it's not actually useful to have that anywhere. Yeah, let's just get rid of that. That's not called on. This should build without that. Yeah. So then that's setting up the page tables. Now, the next thing that we have here is a utility function for translation. So when you can ask the hardware to do a translation for you, and this is useful both for the hypervisor, but also in this case, it's actually used for translating guest addresses, like through the guest page tables. So the CPU can do that for you instead of you having to implement all this page table stuff by hand. So this is actually useful for debugging when I want to translate a guest address, or when I'm getting a guest address, I need to translate to either an intermediate physical address or real physical address to then do something useful with it. So this can handle both. This can handle reads and writes, and then decide whether it only does stage 1 or stage 1 and 2. If it only does stage 1, you get an intermediate physical address, and it doesn't go through this whole page table thing that I set up here. It only uses the guests page tables. And this is a special ARM instruction that does that for you. So this is just a helper for when I need to translate a guest address. Then this is the page table walk function. This is how I look up stuff in these structures that I built back here. So this is the same thing the CPU is going to do, but because I need to be able to look up stuff for software page tables, which the CPU is not going to do for me, I still need to implement this function. So this is how a page table walk works. Basically, you take the input address, you take the high bits, which define the index. This is, by the way, a giant buffer overflow, so I probably should have that. Because otherwise the guest can probably just... I mean, this is not intended to be a secure hypervisor, right? So I make no claims whatsoever as to the security of this hypervisor, but still, it's nice to have asserts for this kind of thing. But yeah, you look up the first index in the top-level page table, and that gives you a page table entry. And then I have these macros that look up what kind of thing it is. So if it's not a table... someone mentioned, yeah, AT produces a fault error for SPT. Yes. So address translate it doesn't return a page table entry. It returns a fully translated address. So if you have a unmapped entry in the page table, it just returns a fault. So you can't use that to actually look up page table entries. You use it to do a full translation if it's not something the hardware considers a full translation. It just tells you there's a fault. So I have to do it manually here. So this is just saying if it's not a table, so it means that it's a direct map of a block. Then if it's a hardware block or if it's a software block, then it adds the lower bits of the address, which means that it directly translates the virtual address bits into the translated address bits, because it's a whole block of memory. I also just realized that for software blocks, this is not going to add, it's only going to OR, so they do need to be aligned. So yeah, they wouldn't need to be aligned for sub pages, but they do need to be aligned for software blocks. I probably should change this to a plus, actually, and then it won't have to be aligned, but that's another little bug fix. I think that'll do the right thing, yeah. And for hardware block, L3 align mask, yeah, I think that's fine. Yeah, that should be both of those. So if it's a whole block of memory that is already translated, we don't have to go into another page table, so it just returns it. Otherwise, it looks up the next address. And in this case, it definitely is already masking, so this is not an overflow. And then this means that this is a table. So that's a pointer to the next table. It can just look up the index in that, and that gets you the next level of the page table entry, and then it's the same story. If it's not a table, if it's a software block, then let's make that a plus. Otherwise, if it's a hardware block, it gets rid of some annoying bits that we don't need, and then it adds the lower bits. Kind of like just realizing, is this actually work? I think I need the L2. I think I need this code in here too, actually, or is hardware block. Yeah, I think I should need. I don't know if we have lower. No, it should. Yeah, actually. I guess the align mask. I know, but I think there's no lower attributes for that. Oh no, sorry, that's the address. No, that should be fine. That's the address. Yeah. Sorry, it needs to clear the attributes in this case. But it should do that. I think it should. I think I should change this actually and put it in here too, and that way I can have the plus. I can just do it like this. I think this makes more sense. And then that can use the align masks. That's the other nice thing about reading the code, right? Is I find bugs. I'm not. This shouldn't actually matter, but it's probably good to. It's probably good to do it like this. Hopefully, I didn't break anything. I'll check the disk later. But yeah, I think this actually works a little bit better for what I'm trying to do. Yeah, and then it clears some bits and puts the remaining address bits from the virtual address, and then that's the address. Otherwise, then it has to be in this case, it has to be a software table, because if this can only be a table if it's a software page table entry, like the macros here take care of all that. So in that case, it has to be software. So it just takes the mask and it just returns the page table entry. Oh wait, hold on. I just I'm thinking about something for a second here. If it's a software, yeah, if it's a block, it should still use the plus. And those are just the attributes, right? Yeah, it should be fine then. Oh no, that's just because of the because it has the address there. But yeah, it still needs to do that. Yeah, so I think that makes more sense. But not that this really matters, because in the case of the hardware entries, it still does that. So yeah, in this case, it just returns the software page table entry. And because this is a level 4, there's no offset needed, because this already points to the finest granularity. So I can just return it directly in the last case. So that's another helper function that just does the same thing the CPU does. So we can look up at the actual the page tables, and we're halfway through the files. We're getting there. So I'm going to skip to the end now and look at what actually happens when the guest handles a data abort. So the first thing it does is it gets information about the exception, the syndrome register, and the fault address register tells me what the guest was trying to do. In this case, the fault address register is a virtual address from the guest, so I have to translate it to an IPA. There's actually a register that tells me the IPA directly. I forget what it was. But I only realized that after I had already written this code, and yeah, PAR, no, it's HPFAR, that's what it is. But you still have to like shift this and add part of the far and whatever. So I forget, I think I never tried using it anyway, but it doesn't matter because HV translate does the right thing anyway. So we get the virtual address from the guest. We translate it only through stage 1. So this is the IPA that we want to look at. And then hopefully that if that fails, that's a problem with the guest. So hopefully that never happens. Because in that case, the guest should fault, not the hypervisor. So that should never happen. And then also hopefully it's never larger. So yeah, I do have a a check for this, so you can't actually overflow it, but still, it's nice to have the assert up there. And then it calls the page table wonk function that I just went through. So this looks up the page table entry. If it's completely unmapped, then it just returns false, and that basically means the guest tried to access something that we don't expect it to access at all. So either I messed up in the hypervisor and forgot to map something, or the guest is buggy. Then, if it's a hardware page table entry, that shouldn't happen, because this means the CPU should have handled this already. So that means that something is weird, and we're just going to go to the Python. This usually happens when I forget to flush the TLBs, which I haven't added to HV map yet. I need to add code to the map function to flush basically the cache for this page table stuff on the CPU. If I don't do that, then it's still using old data, and then this happens. I need to add that later. It only matters if you're changing these mappings while the guest is running. And then if we get here, this should be software. So hopefully at this point, it's a software emulation mapping, so we can do everything we want to do. So there's a target and there's a physical address, which is possibly a physical address if this is that type of page table entry, which is the target plus the low bits of the real address we're accessing, which in this case can be the far because the low bits are never translated anyway. And then this is the instruction in the guest that faulted, the address of the instruction. So we translate that too, which hopefully succeeds, and then we can read the instructions. So this is the opcode of the instruction that faulted. And then the exception information tells me if it's a write or a read. So if it's a write, then we can emulate the store, which means this is going to look at the instruction, figure out how it works, what data it's trying to store, and get that data into the value. And also what width it is, like 32-bit, 16-bit, 128-bit, that kind of stuff. I'll go into that in a second. And so once we have the data that the guest is trying to write, then it looks at the type of and the flags in the page table entry. So if we are tracing writes, we're going to emit a message to the Python saying that the guest performed one of these. So every time you get one of these MMIO R something, or in this case W something, that's this code here that is sending all this information off to the Python so that it can show that. And then in that case, it would be a write event. So we'll look at that later. And then it looks at the actual field type, so it figures out what it has to do with this address. So if it's a proxy hook, then if it's a read hook, it's the same as a write hook. So the only difference is that if it's a read hook, we just pass through writes, but in that case, the physical address is we can't map to a different address, so it's just the intermediate physical address. And then it goes to the same map case, which is just calls a write function that writes data to that address according to whatever width we got from the instruction. And if it's a hook type, that means it's going to call the hook function, which is encoded in the page table entry, and it passes the information. It gives it the value. This is an array, so it's a pointer, so it can write the value there. Sorry, no, it's a read. So this is sorry, I'm confused. This is a write, so we're getting the value from the guest, so that this is going to write to the hardware, so it's reading from there. And the true is the write, not read flag, and the width. And then if it's a proxy hook, it's going to remember that structure I mentioned earlier that tells the Python why we're running the proxy. Well, here's a different version of that, which tells it, hey, the start reason, in this case, it's not a generic exception thing. It's actually a hypervisor, a more specific hypervisor feature, which in this case it's a VM hook. And the metadata that Python gets for that is some flags telling you that there was a write, and the ID that is some number that Python can use to figure out what function to call, the address, and the data. Then this is for the write case, and then the read case is the same thing. It has to emulate the load first because we need to figure out what the width is before we can do the read. So this is like a temporary thing with no data. It figures out the instruction and the width, and then it's the same thing here. It just goes through the different kinds, and it does a read, or it calls a hook, or it calls a Python hook. And then finally, because now we've read the data, we can emit the trace, one of these MMIO reads, if it's a read. And then we can actually finally emulate the load and get the data into the CPU instruction, into the registers. And that's it. That's how you handle a fault. So let's look at all these helper functions. There's PA write and PA read. So when you have to do a write or read in hardware, it's literally just checks the width, This is in terms of the bit shift. So 0 is 8 bits, 1 is 16 bits, 2 is 32 bits. So it's just doing a harder read or write. The same thing I would do from the console here, right? The read 32 thing. It's the same function as this. And it just passes through. That's all there's there. And I do support up to 128-bit reads and writes because we do have to emulate those sometimes, like pairs. And same with the reads. So, and as for the emitting the MMIO trace events, this is a different proxy feature. There's I can just go over this real quick. Basically, the messages that can be sent over the interface to the Python code is all of these. So there's a NOP that is actually it's actually used for features now. Proxy means I'm getting a request to run a proxy function or sending a reply from a proxy function. There's memory read and write, which are special cased, and then boot is when the C side is asking the Python to start running some kind of hook or that we're starting the proxy now. And then there's this event thing, and the events are asynchronous. So the Python is not replying to these. The Python side is just going to parse them and do something with them. So that's how we get some performance, right? This stuff doesn't block until the Python deals with it. It's actually put into a big buffer and streamed into the Python. So as long as the Python can keep up with the data volume, there's there's very little overhead. This is basically just putting into a big buffer. So what this does is it sets the flags with some information about the trace event that happened, and then it basically just copies the data. In this case, if the width is more than, because we can only send up to 64 bits at once with these events, if it's more than 64 bits, then it gets broken up into multiple events. So that's how you get these. Did it just crash? I think it just hated me there. I think I know what happened. I think it tried to sleep, and we don't support that yet. The hypervisor does not support sleep mode, so this did definitely break the hypervisor. I should change the system settings so it doesn't do that. But if I go, I think we're not going to get any. And we're not going to get any 64-bit one. Oh, there's some here. Yeah. So these pluses mean that there's more than one. So in this case, there's like here, right? It's a 128-bit write, so there's two adjacent addresses, and really this was one instruction from the guest, but because the format only supports 64 bits at a time, it shows up as two. But this little plus here tells me that they are paired. And so that's the tracing. And then finally the emulation. So this is the part that decodes the instruction from the guest and figures out how to emulate it. So I don't support all possible load and store instructions. I only support the things that macOS uses so far, which is most of the basic ones and then some really weird ones. For loads, there's like indexed loads and stores, signed and unsigned. I'm actually not confident that this code is bug-free. I'm sure I'm going to run into something stupid that I made here at some point. I've already run into at least one, but yeah. And it has to support the 128-bit pair instructions, and for some reason, it actually uses like SIMD, like floating point loads from MMIO space for some stuff. I don't know why, but it does. So I have some special functions for here that where are those? Utilasm, I think. Yeah, I have some functions that just dump all the SIMD registers out, and I use these for when I want to read and write them from the Python side, but also here I just read it, change the register that needs to be changed, and put it back, and yeah. So there's a few of those, and for stores, it's a lot easier. Thankfully, there's not nearly as many variants of stores because there's no signed and unsigned and any of that for stores. So there's only like 5 different cases that I have to deal with. And this is the other way around. It'll take the instruction and it will look at the register value and then spit it out to the hardware. The only interesting thing is that some of these instructions have pre-post index with update. So in that case, I have to also modify the index register with whatever offset, because I have to emulate the whole instruction. So I have to emulate the store part and the update address register part. So that's done here. And I think that's mostly it. Yeah, we got through the whole file. So congrats. That's the most complicated part of the hypervisor. What was that? I think that's fine. Yeah, so let's see if I broke any of this. Let's run that again. And chain load. Run the hypervisor while we go to the next file. Okay, looks like it's working. All right, let's see if it boots. Hopefully it does. So yeah, that's the bigger part of the hypervisor. So I mean, it's not that complicated when you probably think of a hypervisor as many thousands lines of code and QEMU and that kind of thing. It's 800 lines of code for the biggest thing. It's really not that bad. I also hope that sort of this. I don't need any of that. And hopefully don't need any of those. Oh yeah, these are just comments. That's fine. I hope that this is helping people understand how hypervisors work, right? This is sort of the minimal useful hypervisor that serves a purpose in a way. So okay, so we've gone through exception handling. We've gone through the virtual machine. There's not much left. Let's look at the watchdog timer. So one issue that I had is that debugging the hypervisor is a pain, because if the guest does something that breaks the hypervisor in a bad way that I can't log in, an error about, then everything stops, right? And the even more annoying thing is that actually, I should go into the timers a bit later, but basically the hypervisor is running 1,000 times per second, is breaking, and the hypervisor has to deal with the USB hardware to be able to communicate to the host. So what I do is I hide that hardware from the guest. So the hypervisor has exclusive access to the USB hardware, only to the one port that I'm using for the hypervisor. But it has to, because I'm not using interrupts because it's quite annoying to share the interrupt controller between the guest and the host. Instead, I'm just pull. So 1,000 times per second, I just check to see if there's any USB traffic and handle it. And that stops if the hypervisor stops working. So USB breaks, and Python doesn't not only get any new data, it actually just hangs if you try to write, or you get USB timeouts. Everything goes wrong. So what I had an idea is that I can start a watchdog in a separate CPU core, because I have 8 CPU cores. So why don't I just start another CPU core and just have it in a little loop? And that loop is checking a variable that stores the latest timestamp at which the hypervisor did something interesting. And if this ever stops incrementing, then I know the hypervisor is stuck. And so this is sort of a panic mode where whenever that timeout happens, it will look at those breadcrumbs, and that's the logging thing I mentioned. So every time I call that breadcrumb function, it stores one character into this 64-bit integer. This is it's like a little tiny ring buffer. And then if the watchdog barks, it will dump those out of the serial port. Just in case USB is broken, I will at least get these strings out of the serial port. I do have a serial cable. I intend for this to be useful without a serial cable, but for level debugging, it's still better to have a serial cable. And so then after that, I run the proxy again. So if I'm lucky, the USB hardware isn't actually broken, and I can even now this is running the proxy in a different CPU core. This doesn't work at all if the main CPU core is already running the proxy. Like if the main CPU core is halfway through the USB code, and then I try to run the proxy from the other CPU core, that code is not reentrant. So like if the main CPU is in the IO functions, this is going to break. But if it broke in the hypervisor functions, then it's fine. And this CPU core can take over the hardware and run the proxy, and with a special code that tells the Python to go into a panic shell. And then I have some scripts that I can use to inspect the main CPU and what it's doing, because there's some debug hardware that I can use to find out like what the program counter is and things like that. So it'll run the proxy, and if you quit, then it's time for a reboot. We can't recover from this. So yeah, basically, when I start the hypervisor, it resets everything, and it calls that main function on a separate CPU. I have SMP code here for calling things on other CPUs. There's a little like spin table thing going on. This is not hypervisor code. This is the general. Like in this stream, I'm not going through all the scaffolding that I have in Mini to make this all work, because that would take forever. So I'm focusing on the hypervisor. But if you're interested in this other code, feel free to look around. I like to think Mini is not terribly complicated code. I like to think that it's all fairly readable, and you know the names and the function names, and there's some comments and stuff. So hopefully it can be educational. But yeah, like it calls this function on a different CPU core, and then that just loops while it's active. If it's enabled, it will fetch the timestamp, and there's some memory synchronization involved, because otherwise you can have race conditions. It checks the current timer value, and if it's more than the timeout time has elapsed, then it calls the bark function. Otherwise, it just waits a millisecond, and every millisecond it checks again. And so when you pet the watchdog timer, it updates the timestamp, but you can also suspend and resume it. I suspend the watchdog timer around Python proxy boot calls. So if I'm breaking into Python code to handle something, obviously the Python code can take as long as it wants to handle it, so the watchdog can't be active then, because then it would fire. So I can suspend and resume the watchdog around any call that calls Python, but also around the MMIO trace calls, because if the buffer is full, those can take a long time to process, and I had issues with those causing timeouts. So anytime it interacts via USB, it has to suspend the watchdog timer, because otherwise it would break. And that's also important because, as I mentioned, if this actually tries to run while the main code is in the middle of USB code, that's all going to explode. And yeah, and that's really all there is to it here. And there's a stop thing to kill it if you really want to kill the hypervisor. So I should mention interrupt handling, because that's where the timer stuff is. So if I go back to the hypervisor main code, the start function will start the watchdog timer, which is what you just looked at, and then arm tick. What arm tick does is it sets up the timer, and in this case it's the physical timer, but because this is the hypervisor, due to the register redirection that I mentioned, this actually goes to the hypervisor timer, and then that gets set to fire at a given number of cycles later, and it gets enabled. And in this case, the tick rate is 1,000 times per second. There's a reason why it's that high. It's an unfortunate reason. So then after doing that, it enters the guest. And so what's going to happen is the timer is going to fire. And here in the FIQ interrupt handler, the timer gets processed as an FIQ. And so I check if the hypervisor timer is firing. And if it is, I call the hv.tick function. And then I arm the tick for the next time around so that the timer fires again in another millisecond. And again, going back to the main function here, the hv.tick function will pet the watchdog. So this is how I make sure that I'm still alive, and also handle any USB events that we might have. This is not waiting for the Python. This is just handling like the USB protocol. So like sending and receiving data as required. But this is how a break is implemented. So how, if I hit Control-C, I can get a shell. If I get any data whatsoever from Python in the buffer while the hypervisor is, otherwise running the guest normally, then it breaks into the proxy with the user interrupt reason code. So the way Control-C is implemented in the Python is it sends 1 byte. It doesn't matter what, it's just 1 byte. But that's enough to get the hypervisor's attention and break into a shell. Again, we'll look at the Python site later. And so there's the vtimer is used for like customizable, like if Python wants to have a timer, I can use that. It's also used as a very dumb, not really single step function, more like step a bunch of instructions, like, step a few cycles and then break again. And then these other branches are checking the performance counter registers. These are interrupts that have to be sent to the guest or dealt with somehow, and so that's handling that. Sort of virtualizing it with PNC pending. And also for inter-processor interrupts, again, if that's pending, then we clear it, but have to keep track so we can virtualize that and tell the guest that it's pending. Unfortunately, the guest timers also end up trapped because it's an FIQ. And unfortunately, I can't actually trap the guest timer registers because the ARM architecture doesn't let you do that. There's an extension for it in newer versions that allows it, but the one that the M1 implements does not have that exception. So that makes virtualizing FIQs for the timers actually impossible to do properly because I get the interrupt, I have to clear it in the timer because otherwise the it'll just loop in the guest forever. But then I've cleared it, so how, if I clear it, how does the guest know that it's active? So there's actually a mask register I can use to make sure it doesn't fire. But then, okay, I set a virtual interrupt for the guest to handle it, and the guest handles it. But because I can't trap the registers for the timer, I can't get a trap when the guest has finished handling the FIQ. So there's no way for me to re-enable the FIQ and unmask it because I don't get a signal that tells me that. And unfortunately, there is no way around this. There's no way for me to trap the timer registers. There's other registers I could trap. I might try doing that. Like there's some things the guest does, not because it has to, but because that's how macOS works. After dealing with timers that I can use to cheat and sort of deal with the timers then. But there's no sort of fully correct way to do it. So unfortunately, what I end up doing is that if 1,000 times per second, I check the state of the timers and I update the interrupt. And I unmask it if it has to be unmasked and the guest has handled it. So that's what this function does. Is if the timer is firing and enabled, it sets the FIQ as pending, and it disables the it masks the FIQ so it doesn't fire anymore. And so this is getting sent to the guest, but no further FIQs can fire. Otherwise, it re-enables it so that the next FIQ properly fires at the right time. And the same for the virtual timer. There's 2 timers. And actually, I can trap one, but not the other. But the one that macOS uses is one I can't trap, so it's not useful. And then if that is pending, it sets it to the guest and tells the guest that there's an FIQ pending. Otherwise, it clears it. So unfortunately, I have to poll to make this work. It's pretty sad, but there's not much I can do. I think if I at least enable passing through some of those other system registers and enable trapping, then it'll probably improve performance by dealing with this more correctly. But yeah, kind of unfortunate design decision of the ARM architecture and of how Apple made these timers work, that there's no good way to do it. This doesn't affect normal, like non-macOS guests using... ooh, something rebooted there. Oh, I think it went to sleep again. Probably, yeah. I think it went to sleep again. I should figure out how to change the This settings doesn't do that. But yeah, no, other OSs will use the timers with a different interrupt controller, not the way that Apple uses it, and that's fine. You can get a message when the guest clears the interrupt and then deal with it that way. But unfortunately, it doesn't work with the way macOS does it. And I think that's it for the exception handling. That's pretty much everything here. The synchronous FAQs. So not much more left on the C side. There's a virtual UART. It's very simple code. It only supports the transmit register and the status register. That's all it does. I mean, the guest sends a byte out the UART. I send it out of the virtual I/O device. That's it. This is not a fully correct UART implementation. This doesn't support reading. I want to implement that later, especially for Linux, but it's not done yet. And so this uses that map hook thing I have, right? It sets this function as the hook for the UART address, and this function just checks the address that is being written to or read from, and does something with it. This should be more complicated once everything else is implemented, but you know. So then, and then, yeah, there's AIC. This was actually not part of the hypervisor, during the previous stream when I made it work, but this has been added more recently, where it can trace the interrupt controller, not the FIQ, the IRQ event register, and basically the point of this code is that I can filter which interrupts to be traced by Python. So instead of tracing all the interrupts, there's a bit mask here that tells it which interrupts the Python side is interested in, and only those get sent. So that works. And again, it's something you can just enable, and it starts hooking with a hook function, and then that'll just check to see what the interrupt is and emit an IRQ trace event, which is yet another type of event that can be sent to the Python. So that's pretty much that. So I guess it's time to look at the Python side. So we did pretty much go through the entire code. It's only the header file left. So how does this all work with the Python? Well, the Python side has all the proxy handling in it, which we're not going to go into. There's a lot of code here, actually. Let's open all these files. But basically, this proxy thing implements the low-level protocol for talking over the USB serial port, and the checksums and all that stuff, and there's handling replies, and the useful thing is this handle boot thing, which can be used for other code to register handlers that get called whenever there is an event from the target that says I'm running the proxy loop again. So whenever the C side needs to call that, whenever the C side calls this hv.exec proxy thing, this UART proxy run code, that ends up here. That looks up what the correct callback is for the type, for the reason and the code, and then calls that Python function. So that's how that gets handled. And then events are for the MMIO trace and IRQ trace, and it's the same thing, except those are asynchronous. So there's no reply. It just calls it and keeps going. And this is actually handled in the reply loop. So remember, there's a start call that the hypervisor that starts the hypervisor, and then that's going to be waiting for the hypervisor to shut down. But while it waits, it might get a message saying, hey, something needs to happen, and then that also recurses on the Python side. So both the C side and the Python side are reentrant in this sense. And again, it's designed to be fine. I think you probably can't read the Python much there. So, but anyway, that's just the proxy thing. You don't have to worry too much about that. Why is that not zooming in? Oh, no, it is. So yeah, again, I'm not going to go through all this code for the proxy because there's a ton of stuff here. But basically, it's yeah, all of those functions have codes, and then there's Python wrappers for all those functions. Oh yeah, one thing I didn't mention is the guarded mode thing. Apple has a feature called guarded execution, which adds exception levels to ARM, and so you have GL1 and EL1 and GL2 and EL2, and so I had to enable all that to make the hypervisor work. And That also means that the hypervisor gets called in both GL2 and EL2, and the registers storing the context to return to are different. So that's why I have all these wrappers that look at the right register. Guarded execution is kind of a whole different topic, but Sven wrote a very nice blog post about it. He worked out most of how this all works and implemented most of the core code in Mini. So making it work in the hypervisor was not very hard, other than finding this register, which I didn't know about, which caused me quite a few headaches, and the general GL thing. You remember the pan thing I mentioned earlier, where that was breaking everything. These MSR pan things used to not be there, so even when this was all initialized in Mini, the exceptions went to a different place when here. But the debugging logging didn't work because of pan, and that took forever to figure out. Yeah. So that was annoying to figure out, but isn't actually very complicated to make work once I figured it out. So basically, the initialization here will set the exception vectors also as the GL2 exception vectors. Again, this goes to 2 because of the register redirection. Have I mentioned this is confusing? So yeah, so the same code handles both GL2 and EL2, and is basically these functions just wrap and figure out what which the right register is to use, and the Python doesn't really care if it's GL2 or EL2. So Python side. So let's skip a bit through all the hypervisor, all the non-hypervisor stuff, and look at just the hypervisor code. So this is basically a lot of helpers and useful things to talk to the hypervisor. About 800 lines again, but so if you look at the initialization, a lot of it has to do with setting up the guest and loading things. So when let's look at the client first. So if you open up run guest.py, which is a lot simpler. This is the script that I run to boot the hypervisor. Let's do a start here and see what happens. What ends up happening is this initializes the interface, and there's a thing to make Mini use only 128 megabytes of heap, because otherwise it has like several gigabytes. But we run the guest in separate memory from the hypervisor, of course, so I don't want to use too much RAM. And it sets up the boot. So basically, it instantiates the hypervisor. It calls the init function, which does this. First, it loads the Apple device tree that we get from the from iBoot, which describes the real hardware, and we make a copy of that and parse it so that we can make modifications. Then we check what device the hypervisor is being accessed through, and that's going to be used later for the tracing. And we get the boot arguments from iBoot, and we're going to make changes for all this. So this is basically copying the state of the real boot information, and we're going to make changes for the guest. And then there's a device address table, which is what's used for MMIO trace to tell you what device each is. So that's there's another function that just deals with all of that, makes a nice lookup thing. There's actually a whole data structure for this that is pretty nice, like a range thing. Then it calls the hv.init, which that goes here, right? So just all the .p, that's the proxy. So anytime you see self.p, that's calling a C function in the guest. In this case, hv.init here is calling this hv.init function in the C code. So hopefully you can see how this is all like remotely calling functions on the target. This is also, of course, also calling, like this will be a memory copy and stuff. There's utilities that do a bunch of things behind the scenes, but I'm not going to get into all the details. And then this sets the handlers, right? So what I mentioned, that whenever the guest whenever it has an exception that we haven't handled in the hypervisor, it ends up here. FIQs can happen during the hypervisor, though this is actually used. This can't actually happen, but because we always mask interrupts. But I might make that happen. I might allow that in the future, so it's good to handle it anyway. And then these are the specific hypervisor. To be honest, these are also hypervisor things, but I just kind of called it exception lower. But these are the more specific things. The user interrupt, if there's a hook for the VM subsystem, virtual timer, or the watchdog timer part. And then for the event handlers, it can be MMIO trace or IRQ trace. So the first thing the hypervisor does is map all the hardware directly, so it doesn't trace anything. It does a pass-through. And then there's an IRQ trace thing here. This is going to go away. There used to be a bunch of junk code where like I would reconfigure the hypervisor. Let's see if I can turn off sleep mode so this doesn't crash on me again. But I've been moving sort of hard-coded hack and edit code here to I have these scripts now where I can basically run a little Python script that is in the same context as the REPL shell that can configure the hypervisor, right? So if I want to trace just the GPU, I just call these trace device calls and it traces the GPU. If I want to trace everything, I trace everything, but then undo tracing for a few devices because that's because they're pretty noisy, and then make sure the virtual UART still works. So let me see if I can fix that real quick. Oh, it's still booting and stuff. Kind of slow. So yeah, this is going to go away and it'll be another thing that you can call from here. But yeah, then it configures. So the hypervisor initializes the configuration register. This changes a few settings. In particular, it makes sure that FIQs are redirected, so they handle those in the hypervisor. And then this is that register that Apple defined that gives me fine-grained traps over other features. So in this case, I want to trap the CTRs, the hid registers, which are hardware configuration, the core configuration registers. I need the IPIs to virtualize them. This is actually the Miracles exploit mitigation. If you trap this set, that the Miracle register is one of the ones that is trapped by that. And I also need to trap the performance monitor registers because that also needs to be virtualized. So, I mean, this could be moved to the C code because it's basically required anyway, but it's nice being able to turn things on and off in the Python. Then I have to enable some Apple magic stuff. The Apple AMX, like matrix extension functions, have to be enabled in the hypervisor for them to work in the guest. So I enable them in the hypervisor. This is another Apple thing. They have pointer authentication with a machine key, which is like a randomly generated key in the bare metal, but for a VM that's actually configured by the hypervisor. So if I don't set something and turn it on, then the guest will just wait forever for this to be active, which it never will. So this also took a while to find these registers because this is not documented anywhere. But thankfully, I could find it. And then we map the UART, which is just calling that function in the proxy. But what it does is it looks at what I/O device we're connected through to the like what USB port basically we're plugged into to talk to the target right now, and it looks up the secondary interface, which is the one like there's two virtual serial ports on the USB cable. So the secondary one is used for the virtual UART. And this is hard-coded right now. I probably should eventually look it up in the ADT, but I'm kind of hoping Apple never changes the address of the serial port because it's convenient to have that fixed for debugging. And then it has to, this is another Appleism. This is weird. This has to be enabled in the guest register, and then the hypervisor traps it. I don't know, it's weird. If I don't do this in the hypervisor, then the guest will also just panic, expecting it to be turned on. And then finally, it sets up the ADT. So setup ADT is what actually modifies all the hardware config that I mentioned, that I showed you at the beginning of the stream. So there's a little bit of branding here. I changed some of the branding. So if you go, I can just show you that. If I go about this Mac, not system preferences. I also want to do that, but, and now we're slow. Okay, I'll give you a second. But yeah, it does that. Yeah, so I also want to change this later once I make it not crash, but right now I've disabled both USB ports from the guest. I will only disable the hypervisor one soon. And that basically has to remove all of these hardware elements in the device tree that are all specific to one of the two Type-C ports on the Mac Mini. It also removes all the, CPUs 1 through 7, leaving only CPU 0. But yeah, here we go. About this Mac. So yeah, if you're watching in full HD, you should be able to read that this says the CPU, the chip is the virtual Apple M1 running on the mini hypervisor. So I think I can zoom in with this keyboard, but I think you get the idea. And yeah, this is old stuff. But basically, it removes hardware that the guest can't have access to because we're using it instead. So that's the initialization, and then the run guest thing. It can it configures the boot arguments, which is just like, it gets passed as the set boot args thing. It's just changing the boot arguments in the structure for that. And then it finally calls load macO. And load macO is actually loads the guest kernel. So it loads the kernel. I have a parser for macO data format, and it can handle the symbols and stuff. And so it keeps a table of those so that backtraces work. This isn't used anymore. This is I should just delete it. I had an experiment about patching the kernel, but this isn't actually used. It's not called, so I should just delete it. But basically, the macO code has a function that can create a single memory image for, control mouse wheel zooms in macOS, but I don't have a mouse wheel because this is a trackpoint keyboard. So, so the I have the middle mouse button, but I don't think that actually works. Yeah, no, it doesn't work. It's actually a middle mouse button. It's not a. It's not a. It's not a real scroll wheel. So. Yeah, so this basically does a virtual load of the whole kernel in a block of memory, and then that can get uploaded later. There's a few things that have to be moved around. The secure enclave firmware has to be moved to be accessible to the guest, and then I need to put the boot arguments somewhere. So this is setting up memory for the guest to run, basically. It figures out what the virtual addresses are, and since there's KSLR, it gives it the right offsets for that. And the entry point is going to be, based on the entry point of the file. So this is all like sort of memory, building the memory, putting the kernel in memory and dealing with all this stuff that has to be in memory for the guest to access. And then finally, it maps the, in this case, actually, I'm mapping all the low physical memory, though I don't think I actually need this. I should try without this line, but basically it maps all memory until mini, which includes memory used by hardware. And again, I don't think this is actually needed, but it would be good to check. And then it maps the physical memory that the guest is supposed to see. So there's some minimal security that the guest is not allowed to write over mini. And then it actually sends the kernel to the guest and copies a few things that need to be copied to different places, fixes up a few addresses in the device tree that need to point to the right things, and then finally sends over the device tree so the guest can know where everything is. Again, fixes the boot arguments, like the memory pointers and everything the guest has to know to boot, writes it down, and that's that. So, fairly standard sort of, booting an OS thing. Then the next thing this does, after possibly running some scripts, is this calls hv start. And so the start function will disable any IO devices that Mini is using that is not the current one. So like the frame buffer and the secondary USB and anything that, it leaves only the current. This is because, Mini supports you plug into either USB port or serial, but once we're running a hypervisor, we want to disable everything else and just restrict it to one. And then this is used because otherwise the guest is happy to turn off the clocks or power to the serial port that we are trying to use, and that's not nice. So I have a hack here with some hard-coded junk that disables those so that it doesn't break the hypervisor. This eventually will probably be refactored into something a little bit smarter. This is what makes the logo cool. And then it shuts down the frame buffer, which actually puts the logo back on the screen, the Apple logo. Mini stores it and then restores it later. Then I have to enable SPR and GXF, the guarded execution stuff from Apple for the guest to work. So that gets enabled here. And then finally, it starts handling the Control-C on the keyboard and calls the hypervisor start function. It says does not return. It does return if you exit the guest, but otherwise it doesn't return. And again, that hv start thing is here, right? The hv start function here. So again, that just calls that. So when we actually get exceptions, this is very simple. This is very similar to the code in the C side, right? There's a bunch of useful wrappers here, like map hardware and map software, map hook, trace IQ, stuff for looking up symbols, handling MMIO trace that makes that little prints. But basically, for like stuff like MMIO trace, which are asynchronous events, it just parses the structure and prints it right now. So this is going to change soon, because the next step for the hypervisor is to start developing device-specific IO tracing code. So the next thing that's going to happen is I'm going to replace this with a function that can look up the address range in the same thing this is doing basically, but in a different place, so that specific handlers can look up MMIO trace data for specific devices. So for example, I can write an MMIO tracer for the GPU that knows how to handle when the guest, say, tells the GPU to render something, and then it could even do it synchronously. So it could be not an MMIO trace, but an actual Python hook that then calls it and causes it to dump the display, like draw list, the command structure from the GPU, and then I can take that and do something useful. So there's, I can have endless complexity and in investigating all of this. So that's going to be the next step. But right now, all it does is it prints it to the screen. RQTrace, the same thing. It just prints it to the screen. And then this is the hook thing. So when I want to have a hook in Python, it reads the data and it looks up the correct hook. So the index that comes from the page tables is an index into this array, and that'll give me the read function and the write function and some other information. And then if it's a write, it calls the write function. Otherwise, it calls the read function. And if it's the read, then in that case, it has to write the data back to the target so that it can emulate the read. And so this is all fairly, so just to give you an idea of how this works, this is the other way around, right? So when the hook VM, so this is the opposite case where the C code is calling this VM proxy hook structure to start the Python handling loop, and in that case, this is going to go here. So in this case, it's the C code, quote, calling Python as an exception, right? So that Python can do something and then return true, which means that when it returns true, the exception is handled and it goes back to the guest. This is the handle MSR. This is for MSRs that I don't handle in the C code, things that matter less. By default, I actually just pass everything through in the Python. So it gets logged to the screen and passed through. But the miracles register gets skipped. That's the mitigation. At least that one is shadowed, so I don't want the hypervisor to lock anything. And then these registers, I cheat and make them read-only because I don't want it to mess everything up. Let me see if I can fix the sleep thing while I'm here. Turn the display off. No, that's not what I do. Energy saver. Yes, that. Yes, I know it may use more energy with these settings. That's the point. So hopefully that fixes that. So, so this is just checking the MSR information. I mean, this is basically the same code as this, right? The C code looks like this. It checks the ISS. It gets the register that is, and whether it's a read or a write. And this is the same thing. It gets the ISS. It gets the encoding. OP0, 1, 0, and 0, OP2, same thing here. And then it looks it up in these lists. So this Python code basically mirrors the C code. This is another hack that I have in there that I can use to hijack guest exception handlers and trace them from the host. But it's very hacky because there's no clean way of hooking it. So I just pull until I can do it. And again, there's the ELR +4 thing here, which is what happens when it's handled properly, right? So we can very similar code on both sides. This is for the implementation defined things, which is this case, right? So again, this code, same thing as this code. This is for hypervisor calls. These are not used normally, but I use them for forwarding what I mentioned for this thing. Basically, I have a hack where I can patch the guest's exception handlers to cause hypercalls, and I can use this to trap on things the guest is doing. So I can actually show you how this works. If I enable this, then I can, I need to quit and restart everything, but just do a reboot and chain load again. But what's going to happen is that every single guest page fault and every single guest system call from user space is going to end up logged. It's extremely slow. I don't think we're even going to see it finish booting when this thing is turned on, especially because it's going through Python through everything, so it's not even asynchronous. But this was very useful early on while I was debugging the kernel boot, because if the kernel crashed with a null pointer DRF or something, then this was giving me visibility into what was happening. And especially debugger, like if I had a kernel panic, see all these page faults that just get logged like that. If I have a kernel panic with this turned on, it actually triggers a panic decoder in the Python. I have a thing that can decode kernel panics from XNU, and this works even when the serial port is broken. So even before it initializes the serial port, or if it can't use it for some reason, I can still get panic information here. Yeah, so like now it's you're seeing system calls from user space. It's ridiculous. Like this is going to take forever to boot by this, but I mean it's cool that like I can literally see every single page fault and every single system call from user space and like what it was doing and yeah. Let's see if it even finishes by the time I finish talking about this. Mr. Sparkas, can you talk a little bit about how the GPU support progress is going on, how this hypervisor debugger, the focus is to help accelerate the progress review? Yes, I mean, I need this to make the GPU work. There's, as I mentioned at the beginning of the stream, there's two ways to figure out how the hardware works. Either I reverse engineer the macOS code, or I do it this way. And I chose this way because reverse engineering is both more annoying and legally dubious. So the nice thing about doing it, by the way, with this MMIO tracing thing is that it is clean room equivalent. So there's no way for me to commit copyright infringement on macOS code by looking at these MMIO trace dumps. Well, the code dumps, yes, but I mean, it's just exceptions. But this MMIO trace stuff, no. So, the like Alyssa and the other and some of the other Mesa folks have been working on the user space side. So they've been working on figuring out the shaders, how the draw commands work, how to make the GPU do different things. But all of that is in user space. So in macOS, they're looking at how the libraries, the metal libraries in macOS work, how they talk to the hardware. But then there's the kernel side that has to take those commands from the user space and actually send them to the hardware, and also initialize the GPU and deal with virtual memory and context switching and all that. And so that's what the hypervisor is for. So now that we have this, the next step is going to be starting to write those MMIO tracers that are specific to the GPU things. So actually, I'm going to do something more useful than let this never finish, because it's not going to. Let's do a reboot. Sorry, tools. Oh, we don't have. Yeah, those are. Yeah, I do have it there. Oh, that is not executable. I need to fix that. Yes. So if I do a chain load, give me a second. So I have a hypervisor script. I'm going to do the exception handling thing because it's crazy. So instead of trace all, I can do trace AGX. And that traces only GPU accesses. And it doesn't do anything useful right now because I need to add, well, I need to start looking into exactly what those GPU commands are. But it'll give you an idea. So let's let it boot. So while that happens, yeah, so what you saw now with the tracing system calls and page faults, that's this. Basically, I patch the exception table and the guest to hypercall back to the hypervisor, and then I deal with it here. And it's, yeah, this is the debugger thing, the panic. handler. So it was useful at the beginning, but it's not really useful anymore. So and then the moving up the stack, this handles the synchronous exceptions. So if it's an MSR, if it's implementation defined, calls here, hypervisor. Again, that's looking at the hypervisor. It's this code. And then this is the entry, the root method for handling exceptions in the Python. So in this case, there's a here the CPU takes care of that, of splitting it for us. But here the Python, there's a single entry point, figures out what kind of exception it is. In some cases, it'll run VM hooks, or if it's a user interrupt, it just goes into the handler. It just goes into the REPL. And then if it's handled, if there's a SIGINT pending, if I write Control C, then it'll go into the REPL. Or if it's not handled, otherwise it'll and if it's not handled, it'll print the exception. Otherwise, it won't. And then depending on what this just runs the REPL, right? So it restores the Control C thing, and then puts it back after we return. And so that's what that handler is. What does the it just sends an exclamation point to the guest, but that's enough to make it respond. And then also the handle bark. If the watchdog expires, it runs a panic shell, and then it just exits because there's nothing to do there. And then these are our convenience functions. So the REPL has another hack in there where I can, like, instead of putting parentheses around functions, I can just skip that, and it'll run it anyway. So these are just convenience functions for building things and decoding debug panics and stuff, getting a backtrace the BT command. It just keeps calling translate on successive stack frames. That's the hack for patching the exception handlers. You don't want to read through that code. And yeah, like trace device. This is how what I just ran, that trace AGX thing. It just says it looks up a device in Devicetree. And for every register set that it has, it resolves it and then does a map software saying we want to trace reads and writes. Or if we disable tracing, then we just don't. If it's unaligned, it'll still have to be software, otherwise it'll be hardware. And so if I go here, and you can see it's still booting probably. Yeah, still booting. Yeah, it's just getting to the GPU thing now. And you'll see that it's much faster now because I'm only tracing the GPU and not anything else. And actually, I probably want to turn off this PMP stuff. I'm not sure what that stuff is about. I think I used to have that. I can probably just untrace the PMP and that will work. So if I do trace device arma PMP false, that hopefully will take care of that. Yeah. If I just can't, then that'll get rid, because there's like an overlap between the PMP and AGX, and it's annoying. Yeah, so now it's just the AC and SGX. I should just add that here, actually. So you can see all the GPU functions, and so you can see that if I, it's kind of hard to see because of the prints, but basically, like, you can see that there's every time it renders a frame. So it actually doesn't render frames most of the time. It only renders frames when like there's an update. So like when the cursor blinks, so I can hit login, and then now that the spinner is causing it to render frames quickly, and it stops. So you can see how the GPU traffic mirrors the activity in the OS, right? The spinner stops and then the GPU stops, right? So in this case, the ASC is the coprocessor in the GPU. And so you can kind of see in here that it's, I don't have the details. I don't know the details for that source. So you can see how it's doing like 6, 7, 7, 8, 8, 9. Something like there's an incrementing number here, right? And that's almost certainly some kind of message pointer, like some kind of pointer into a list of commands or something. And then or maybe it's an address in virtual memory. And then it's gonna parse that. So I have to work out how this works and then start dumping, draw commands. But you can see how my scroll bar moves whenever like the target is rendering things. Like whenever things change on the screen is when the scroll bar moves. So I can close for example, I can close this and wait for it to finish booting. But yeah, so that's how the tracing works. It just does maps anything that needs to be mapped for that device as pass through or as trace read and trace write. And so the init call in the Python, we already looked at this. And that's basically it. I think that's most of the code. Yeah, load macro. Yeah, that's basically it. So again, hopefully this is not too complicated, and it made sense. Give me a second to show you what I wanted to show you here. Yeah, so if you look at the cursor here, right? I'm just gonna minimize that and open up something small like a terminal. So you can, if you can see my scroll bar there, you'll see that when I drag the terminal, it moves. So anytime it's rendering, you can see. Of course, if I play a video, it'd be constant, right? So you can see how it only renders frames on the GPU whenever you move something on the screen, which is, of course, how you do it in a power efficient way. So. But yeah, I mean, like, I don't know. I know that these writes have to do with the message registers in the coprocessor, but the next step is to start looking into exactly what they're saying and how, how they communicate, and then what the commands are and the structures are and all of that. So, and this, by the way, is a Mesa bug regression, the corruption there. It's already been filed. I might help debug it. There's a regression in the latest point release. So let me look at the comments and just catch up a little bit, but I think we're mostly there. Oh, Thomas asks about how Linux handles high performance and energy efficient cores effectively, or some patches will be needed. Yes, Linux has that, as Cardell just mentioned. So actually, in the Linux device tree, you specify the relative performance of different cores, and Linux knows how to use that information in the scheduler to make intelligent scheduling decisions. So yes, you can give it, an idea of how cores have different performance and different power usage and different latencies, and it'll try to do the right thing. That's already the case because it's used in Android all over the place. So, yeah, I think that's pretty much everything. So, any questions? Anything you want to hear about that I haven't covered yet, or any little specific detail that didn't make sense? I was actually expecting more comments than I got, so I don't know if that means that I explained things properly or that nobody knows what's going on. But hopefully this makes sense. So yeah, let me know. Otherwise, that's pretty much all I got. So the timer thing confused you. Yeah, so the problem is, let's go back to what the timer issue is. Let me just type you, right? So the timer is controlled directly by the guest, but I trap the interrupt, right? So the guest sets up a timer, right? And then the timer fires. Now I'm trapping the FIQ, so the hypervisor handles the timer, and then the hypervisor sets a virtual FIQ, and the hypervisor masks the timer so that the guest, because the interrupts are always enabled for interrupts are always enabled for traps when the hypervisor is trapping them. So if I don't mask the timer, as soon as I return to the guest, it's going to fire again, and we're going to end up in an infinite loop. So the hypervisor masks the timer. So this is fine. And then returns to guest. Returns to guest. And because there's a pending guest interrupt, the guest automatically ends up in the interrupt handler. Guest handles FIQ, virtual FIQ, I should say. And guest clears the timer like IRQ status. This is the problem. When this happens, I need to unmask the timer because the next timer needs to trigger an FIQ, but I can't trap on this. So now the guest returns from the FIQ, and there's no hypervisor trap anymore. The guest keeps running code forever. And the next time, let's call it this, like sets up, basically there's a sets up timer thing, keeps running code, and timer fires, and it's masked. And I can't do anything anymore because it's still masked. So the problem is that I need some way for the hypervisor to trap after this timer gets set up, and yet I can't trap on the timer registers. So what I'm doing now is just 1,000 times per second, I check. And if the timer is set up and not firing, then I unmask it so that the next time the interrupt fires, we actually deliver it properly. That's the problem. And this is not an issue when the guest is using GIC, the standard ARM interrupt controller, because in that case, there's a specific GIC, like end of interrupt signal that will allow us to unmask the timer. But that's not a thing in the weird FIQ thing Apple is using. And yeah, as for Linux scheduling, I actually don't know how the individual processes on Linux do it. Like I know macOS has a process QoS thing where you can ask it to go on the efficiency scores or the performance scores. Linux does have explicit process affinity. I don't know if it has like a sort of softer QoS thing like macOS does, but I would expect it to because again, all of this is stuff that Android has been using for a while. So, like if stuff needs to be improved around here, it will benefit other ARM platforms too. So it would be something that we're interested in for our project, but like I expect other people to care about this too. So hopefully, hopefully we don't have to focus on that for now. But because I do want like Asahi Linux to be efficient and work well on these machines, like, once everything else is taken care of, if it comes down to fixing the scheduler to not suck on these heterogeneous SMP machines, then yeah, I mean, of course, that's something that's also in scope. But I know there's already, I don't know exactly what's implemented, but I know there's already a bunch of stuff there. So hopefully it already works pretty well. Can you talk about the things the hypervisor already helped to reverse engineer? Well, I mean, I just made it work like a week ago. So we just got here basically. We haven't actually, we're going to start using it now. Basically, the hypervisor worked for the first time like a couple of weeks ago, and then I was busy for a week. And this week I'm cleaning things up and building the scaffolding for starting to reverse engineer things with hypervisor. So like right now, I don't think there's any single thing it's helped reverse engineer, but it has helped me figure out things about the hardware that I had to make work to make the hypervisor work. So missing details about GXF and SPRR, those have that has helped in that sense that we've learned things about the hardware by making the hypervisor work. But yeah, actually using the features to reverse engineer GPU stuff and all that, that's the next step. So look forward to that. Yeah, that's what's next to be implemented or poked around. Yeah, what I just said. So the next step is I did this yesterday. Is I reorganized all of this folder tree to use a proper Python module. The reason I did that is I want to have sub modules for like trace graphics, trace, I don't know, sound, trace, the power manager, generic trace for coprocessors. Like I need to have, this needs to be cleaner code now. Basically, no more patching hv.py to do experiments. So that's why I made the support for. I added this yesterday. The ability to run scripts external to the core code base that can configure the hypervisor. So so the next step is going to be adding tracers in a submodule here for tracing different things, and then hooking them up so you can enable them, disable them, and they have dependencies and all this stuff magically happens. So coming from normal software development or basic HV knowledge, QEMU would be a good idea to a good starting point to get into reverse engineering hacking. Well, the hypervisor isn't really reverse engineering. It's for reverse engineering, which is a different thing. But like almost none of what I just explained is specifically reverse engineering. It's a tool. But yeah, every time someone asks me this question, like all I can say is find a project that interests you, that requires reverse engineering, and just kind of learn it along the way. There's like no sort of universal starting point so much as find something that interests you and then dig deeper on that specific thing, right? I think that's how basically every single reverse engineer I know has started. Is there's no reverse engineering. I mean, they are reverse engineering books, but most people I know haven't gotten started reading books, probably for good reason. So yeah, like just find something that interests you. Specifically, right? So, for example, if you want something to do with our project, you could start looking at a specific piece of hardware, right? You could start tracing, I don't know, sound or something. Well, sound is probably a bit complicated, but you could start looking at these numbers here, and at any point you can Control C and change things, right? So, like you can break macOS, right? You can, like, if I take what I did at the beginning of the stream where I was looking at the configuration. If I look at the screen config, if I change that, it's definitely gonna be very interesting. If I set it to like this, the colors should be real funny. Oh, look, it's actually interesting. It actually goes. Oh, I totally broke. Fun. We're not supposed to touch that register, but I think macOS macOS definitely hated me right there a lot. Oh, it panicked. Of course it did. So it's interesting that panicked. It probably something with. Oh, look. Okay, cool. So see, this is actually useful. I think I crashed the coprocessor. I did, and this panic. Oh, this is fun. See, I just discovered something. This just panicked the DCP iPad 13. DCP panic. And so this is a whole debug log from the coprocessor telling me about everything I just broke, which is going to be very useful information. Like the mailbox, the messages that got exchanged. There's a log. Async error info, the L2C. Yeah, these are the MMU thing. I know about those. The timestamp is nice to know. And another log here with more stuff. Cool. So, and then there's the thread that panicked inside the. No, this is the macOS panic. But yeah, like cool. So yeah, that's another way of reverse engineering, I guess, is break it and see how much debug info you can get out of it. So, yeah, interesting. So yeah, there's a task called Terminator. Excellent. But this is cool because it tells me what the DCP is doing, right? So there's a DCP expert, but there's probably also like see DCP AV, DCPQ, IO surface tracker timer, like DPT, XH, CCP, SSH, HTTP stuff there, AV controller, display core controller, global, whatever that is. There's a lot of threads in that CPU. Yeah, authentication HTTP stuff. And some other things. So RTKit, by the way, is the real-time OS that Apple uses to develop all of the firmware that runs on these side cores. So, so there's actually like at least 12 coprocessors in the M1. there's a lot of coprocessors in the M1. Like there's one each for the display outputs, one each for the Type-C ports for Thunderbolt and stuff. There's the system management controller. There's the one for the audio-video encoder. There's the one for graphics, power management, system management controller, the always-on processor, which is like the Hey Siri thing and stuff like that. There's the image processor, which is for cameras, which isn't used in the Mac Mini because there's no camera. There's so much stuff. There's like I think there's the IOP also handles audio, I think. There's the NVMe controller. Yeah, there's a bunch that I can't even remember. There's like a serial input type of thing, like used for I think it's used for sensors. So yeah, there's at least like 12 like secondary CPUs inside the M1, which is like more secondary CPUs than primary CPUs. And most of those are Chinook ARM 64-bit CPUs, which is a small 64-bit core. It's like the Apple Watch core, I think, or similar to that, or maybe an even smaller one. And they run this firmware that iBoot sets up for us. So basically, this is actually very useful because, for example, I was not looking forward to writing code to handle DisplayPort training and like display bandwidth calculations, and that is all abstracted out by the firmware and the display controllers. So it is quite likely that like the Linux driver for handling the display mode setting is going to be a thin wrapper that just like forwards all the Linux commands to this controller, at least to the extent where the APIs match. But that's like I'm actually very glad that Apple is using firmware like this. Like some people hate blobs. I guess I might as well talk a little bit about the design of the M1. Like all of these sub CPUs have IO MMUs, so they cannot compromise the security of the main CPU. So, most of the practical reasons for being wary of proprietary firmware don't apply to the M1 because the firmware is performing a function, but it's not it's not a place where you can like hide a backdoor, right? So, and the firmware is loaded by iBoot and like signed by Apple. So you can't. I don't think we can change most of these firmwares because I think the regions are locked. I'm not 100% sure how watertight that locking is, but it doesn't matter because we can just treat them as black boxes effectively, and they automate a lot of the dirty work around the hardware, right? So like dealing with the display, but also the GPU, like task switching and stuff like that. And Apple has this one like universal interface for these subcores that they use to communicate with them. So like there's going to be a Linux driver for talking to Apple system controller cores, and then that's going to be reused across all of the drivers that have to deal with these things. And yeah, like people have different ideas about proprietary firmware. Like my view is that if proprietary firmware is not a security concern, and if it's doing its job and doing it well, and not crashing and stuff, and implement it properly, then I don't really have a problem with it, right? And as long as it's and also not a distribution problem. So we don't have a distribution problem with these blobs because they come with every Mac. So like our installer can just copy them from one partition to another, and that's fine. It's part of recovery mode, so they're going to be there. Like, it's not expected that users would delete recovery mode because it would break your boot picker and everything. So, and also even though they're signed by Apple, we can use older versions, right? So this insulates us from incompatible upgrades. If Apple upgrades their firmware interface in an incompatible way with Linux, that's fine. We can keep using the old version until we support the changes. So you can dual boot macOS and Linux, and they'll use different blobs and different iBoot 2s. So, upgrading macOS is not going to break Linux, which is nice. So go back to the comments because I kind of digressed a bit. Is it possible to enable virtualized Bitcoin hypervisor? Yes, I mentioned that. I do want to support multi-core eventually. I need to add locking and stuff, but there's nothing that would make it impossible. Is there official docs about device trees? The Linux device trees are similar in spirit to the Apple ones. So if you want to learn about Devicetree in general, look up the Linux Devicetree spec. Just Google Devicetree. It's devicetree.org. So both the Linux Devicetree and the Apple Devicetree are descendants of the open firmware, like Devicetree, not really Devicetree, but like the open firmware API used on PowerPC Macs. So this is why Apple uses it on Apple Silicon, and this is why Linux uses it for ARM these days. But the Apple version of the Devicetree and the Linux version of the Devicetree differ in all the details. So if you want to learn how Devicetree work in general, read the Linux spec first, and that'll give you a good idea of all the concepts. And then you can use the tools in the mini report to dump the Apple Devicetree and in the same format as the Linux ones, basically. And like it'll make sense. Just be aware that like the specific details of like the names of things and the hierarchy and how everything is done is not the same, and the binary format is not the same. So we can't actually take an Apple Devicetree and turn it into a Linux Devicetree, but the concept is the same. So if you understand Linux Devicetree, the Apple Devicetree will just make sense. Would it be worth porting Mini to another ARM64 devices? Yeah, I thought of that. Like Mini is intended as this, Apple Silicon specific thing. And it was always meant like that because, like the idea is that if you want to port it to other hardware, like the proxy stuff is generic enough, but all the details are pretty different. So you would just copy the code base and, change it for whatever. Like Mini was already a port from the Non-hypervisor Mini that I wrote for the Wii, and which I also had gone through using on some like Chinese MP4 players and things. So it's like a code base that I copy and paste and adapt because it's not like the whole point is that it's simple and straightforward. And if you start making it into like a multi-target code base that has abstraction layers for different targets, and it stops being simple and it defeats the purpose. So as a sort of first stage bootloader and tool, there's like a gradient of generality versus simplicity, right? And so like in our boot chain, Mini is the least general and the simplest, and then U-boot is more general but still pretty simple code, and then Grub is like more general using APIs, and then Linux is like runs on everything but is abstracted out to hell and back. And all of this made sense until the hypervisor, right? Like the hypervisor is the first useful thing, very generically useful thing, because not just macOS, you can use it to debug Linux and to debug Mini itself. You can run Mini inside Mini in the hypervisor, and then you can debug crashes like that or get serial port output without a real serial port. And once I implement serial port input, this will be useful for running Linux without direct USB support for development. And also, of course, if it crashes, you can debug it that way. So certainly there's some value in having a generic hypervisor like this for other ARM64 devices, but I don't know how I want to do that yet. I don't know if I really want to start making Mini be, generic in that way, because I fear that it's going to make it more complicated and hard to hack on. And like the whole point is to make it easy to hack on. But it might make sense to abstract out the hypervisor into different project that can then kind of evolve on its own. I don't know. I'm not sure. So, yeah, it's people talking about the specifics and stuff. How's it going on Patreon sponsor support for Asahi Linux? Yeah, actually, I just got an iMac yesterday. I haven't opened it. I haven't opened the box yet. I need to get a VESA arm. I need to figure out how I want to mount it. But I'm basically committed to, as long as I have support, to buying every one representative configuration of every Apple Silicon device, so that I can test on all of the devices. Obviously, right now, there's not much to do on the iMac, but once we start getting more hardware in, I have to test it there too. So, and yeah, as for Patreon sponsor support, to be completely honest, it hasn't really changed much. Like, there was a big, like in December and until January, like it blew my mind how quickly people started supporting me. And then since from January to now, it's basically remained constant, which I'm not complaining about at all. I'm like, there's people dropping out and new people coming in, and the churn has been kind of even. But like, I'm not worried because at the current level, it's more than enough for putting a lot of work into this and buying hardware and stuff. But I'm also kind of hoping that as we make more sort of flashy progress, once we start getting graphics working, which I'm very hopeful for this year. I can't promise anything, but I think we can get a nice GPU accelerated desktop going before the end of the year. So, possibly without power management or whatever, but definitely something that runs and performs reasonably well, and like, it'll be pretty good progress. So I'm kind of hoping that also, once we get to that stage, then maybe that'll bring some new people into the Patreon. But no, like, I'm really happy with the support I've gotten so far, and and I like, I have to thank everyone for making this possible, because it really wouldn't be without that. So looking more at the comments. Yeah, so this is based, as I mentioned, this is based on Mini, which was originally used on the Wii. It's actually based on iOS proxy, which is like an unreleased precursor to Mini that was this same remote proxy thing. And then that got merged with parts of Mini and turned into a Mini port for Chinese MP4 players, which is Little Endian. And so this version of Mini with the ones is a like weird mix of code from the MP4 player port and the Wii stuff that was a bit updated later, minus all the Wii specific things, and then ported to 64-bit ARM and then changed. But if you look at the code, like especially UART proxy.c and this kind of stuff, this is straight from like 2007, 2008 code for the Wii. Hasn't changed. Like, literally, this function is the same and stuff. So, yeah. It was, I mean, we never got around to writing actual custom firmware, but we were reverse engineering the hardware, so it was just kind of fun. So there was like this Sun Plus chipset for MP4 players, and we figured out how to it has like a 2D GPU that can do some acceleration with drawing lines and stuff. And we figured out some of the hardware. I don't remember if we ever got audio working. It was more of a fun project, really. It wasn't like a big thing to actually port a custom firmware or something, but just a random fun thing. Yeah, you don't need to keep a macOS partition around for the blob updates, because it's also in 1TR. So 1TR itself will contain the blobs, and also iDevice restore, which is how you can unbrick these machines with Apple Configurator 2. Like, the way you unbrick these machines is you plug it to another Mac with Apple Configurator 2 and then run it in DFU mode, and it'll update everything and restore everything. But there's one mode, but it only installs like the recovery code. And iDevice restore now implements all of this on Linux, so you can already unbrick and restore these devices from Linux. And I don't know if the only restore 1TR mode is implemented, but if it is, it should be easy to add. And so you could do that to update 1TR only from another, PC or Linux box or anything. And that would give you new blobs. And then you could also just update them that way. But also, we could just have our installer download them from Apple's CDN. I mean, like, obviously, every Mac owner has a license for macOS implicitly, and 1TR is macOS and is fundamentally part of the firmware for these devices. So, we're not going to be distributing these blobs ourselves, and there is no chance of Apple being upset that we're scraping their CDN to download them, because that'd be silly. So I don't expect us to really have any legal issues here. And because this is handled by our updater script and the bootloader, distributions don't have to touch any of this with a 10-foot pole. So, they don't even have to think about any of this. We're going to be dealing with this ourselves, and we can afford to not have to ask lawyers about this, because I know there's not going to be an issue. Does every vendor have their own Devicetree implementation? No, there's only two as far as I know, Apple's and Linux's. The Linux one became the standard everywhere. Like OpenBSD also uses it, and U-boot also uses it. And then Apple had their own thing because like Apple had it before Linux even was using it for ARM, I think. So like Apple's implementation predates wide usage of the Linux one at least. Winnie for Windows on ARM Mini. That's a different story, but yeah, you need a hypervisor to run Windows on M1 Max. But it has to be quite a bit more complicated because it has to emulate a whole bunch of hardware. It's conceivable that the mini hypervisor could be turned into that, but that would be a very different scope. But as far as I know, the Pongo OS people were interested in doing that and having like a bigger hypervisor that can run Windows. So, Sun Oracle has a Devicetree. I didn't know about that. Like for what? Spark? And there's some indications that the iMac can support 2 external monitors. Yeah, I don't know about that. It shouldn't be possible with the M1 because it only has 2 display controllers. But I wonder what's going on there. I guess we'll have to find out. Oh, I mean, open firmware. Okay, yeah. Well, I mean, open firmware is a different thing anyway, but like that's not the Devicetree blob. It's the actual API-based thing, so. Mr. Shrek says, thank you. You're welcome. And Graham Sutherland says, heard from corporate folks that previously using iMacs for their purposes. The lack of Windows compatibility has caused them to have to completely rethink that. Yeah, I mean, Microsoft could make Windows compatible with M1, but it needs changes to the Windows kernel, so. Does Apple ever update the Devicetree blob? Yes. So the firmwares, the Devicetree blob, and iBoot 2, which is the second stage of iBoot, sort of, and also some other like trust cache, define the OS compat layer. So those components come with macOS of any given version and are constant, like they are effectively part of the OS. So effectively, for Linux purposes, the compat layer for all of this, and Mini reads the Apple Devicetree, by the way. So like we will be shipping our own Linux Devicetree, but Mini is in charge of moving some information between them. For our purposes, the compatibility level is whatever macOS version files we are using for that, for iBoot 2, the firmwares, and the Devicetree and everything. And like that is basically one package, right? So you can think of these Macs. I should really use an image editor or something. But you can think of these Macs as having like 2 things, right? So there's like one package is called SFR, and like that's basically the boot stuff. So that will include iBoot 1. It will include 1TR, which includes its own copies of iBoot 2, etc. And that's basically it. And then there's like OSs, right? And you can have multiple OSs installed. And so every OS is going to have its own there's also some firmwares, and then there's going to be rest of firmwares. This is pretty like this. So it'll be like rest of firmwares, iBoot 2, Devicetree. And so the OS number 2, etc. will have that, right? So So for our purposes, like OS number 1 will be, for example, macOS if you want to dual boot. And this will be mini, which then goes to U-boot, and then possibly grub, and then Linux. So, and then number 3 could be something else. Could be another copy of Linux, or let's say that you want to do the correlating units, right? If you don't run the correlating Linux, you should install it as a separate partition because they have their own loader, and it's sort of they live in a different world. So you could triple boot like this, and each one has its own copy 502 with the Devicetree and the firmwares, and this triplet here maps to like a macOS version, right? So we could say that this is the macOS 11.4 version of the bootstrap code, and then as long as we support that macOS version for our boot code, then it will be compatible. And SFR only ever updates. So SFR is system firmware and recovery. You can never downgrade SFR for security reasons, but that's okay because SFR is designed to always be able to boot older iBoot to whatever, all this stuff versions, right? So that's the promise that Apple makes, that they will, well, at least for release versions, because I know for a fact that they broke it with some beta versions, but at least for release versions, the promise they make is that the most current version of SFR will always be able to boot all prior versions of macOS, at least that supported that device. And so for us, that means that once we install Linux with this, we can just not care and not update it, or we can update it if we have a reason to, like bug fixes in the firmware. And then as long as we support those changes, then it's fine. And this separation means that we, macOS doesn't have to care and it can update itself and not break Linux and that kind of thing. Looking at the rest of the comments. The next 64 emulation forum, I actually want to. That's another thing I'm interested in, is in a Rosetta-like thing. Because if I'm going to make an M1 Mac someday or an M2 Mac or something, my main workstation, I need x86 emulation. Not for a lot of stuff, but for a few things. In particular, like running audio plugins and things like that. So I need like Wine that can run 64-bit and at least 64-bit x86 code. And like QEMU can already do that, but it's not very fast. So I'm hoping that there's, more interest in this area in having faster, like a Rosetta equivalent userland x86 emulation for Linux and ARM. And again, if nobody else is working on it by the time somehow my to-do list grows lower, then that is something I'm interested in working on. I actually don't use that many. Like all my music right now, I use 2 or 3. I use 3 x86 VSTs. I use Korg M1, I use Trillion, and I use Melodyne. That's it. So like if I can get those 3 to work, I'm happy. But yeah, definitely need at least those. So, though I mean, it should work in QEMU. Actually, I talked to the average guy, the guy who does the compat layer that I'm using now, and it should actually just work with QEMU user. It's just not going to be fast because QEMU, but I don't think there's any technical reason why it wouldn't just work. But I'm interested in better performance, obviously. Yeah, someone asked about TSO. Yeah, exactly. So YaBridge already does the bit bridging, and it does that by serializing everything into like bitness agnostic formats. So that's why it should literally, like the guy said, it should literally just work. So yeah, I'm just more concerned about performance and QEMU user, but we'll see, I guess. But yeah, Lou asks about TSO. Yeah, so that's easy to implement on the Linux side. And it should be easy to support in user space code. There are questions around the how well it would go down to implement this in Linux as far as upstreaming. But thankfully, it would be a small patch. So it's the kind of thing where we can just implement it in a fork. And I mean, obviously, we're going to be upstreaming everything we can upstream, but it's not the end of the world if we have, sort of a fork with a few extra bits that are not upstreamed yet. And so it's not a big deal if we have like a fork for TSO and cooler emulation, and then if enough people are using it, that helps the case that it should be upstreamed, and then we'll figure something out. So I'm not too concerned about the bureaucracy, and the technical side is not hard. So worst case, people interested will have to run a kernel fork, but it's not the kind of patch that is going to cause big merge issues very often, I think. So it should be fine. Oh yeah, Fex is what it was. I was looking for that. I was looking for that thing. I knew there was a thing. And I was trying to Google it, and then I completely I see the link was clicked. I was looking for this again, and I failed. Yeah, so so this uses the tunk loops for GL and stuff. Yeah, this is what I was looking for, basically. Thanks for reminding me of the name. So I'm interested in how this would work for the average, because it's very much what the kind of thing I'm interested in. So I guess we'll find out. New Firefox tabs? I don't know. Whatever. They're fine, I guess. So yeah, this should be interesting. Okay. Any other questions? Anything else to cover? That's pretty much it. Yeah, this is my broken macOS. But, I can still Control C it, even though I panicked, and still do a reboot and go back. So that's nice. I'm actually pretty amazed that it crashed that badly because I poked to register. Where did it crash? I'm gonna go back to this. Like, what's the actual crash there? It crashed in mailbox. Really? Oh, start frame active. Something about the mailbox, I guess. Task 40. Yeah, that's interesting that died. Anyway. Okay, well, I think we've covered pretty much everything. So, thank you for coming by. And don't worry, there will be more streams and more dev streams coming up. So, everyone have a great weekend. And see you soon. Bye. Someone is asking about STFU. That's STFU. Ooh. Yeah, there you go. See you. Bye-bye.